Picture this, a forgotten warehouse tucked away from the world, its air thick with the scent of aged paper and old dreams. Inside, locked in rusting cabinets, are stacks of technical drawings, their lines and annotations faded but still sharp. These are not just any plans, they are the lost blueprints for engines that could have taken us to the stars, concepts so radical and advanced that they were dismissed, filed away, and ultimately forgotten by the very world that spawned them. For decades, they have waited in silence, holding secrets that are only now, in our time, beginning to make sense. This is the story of those 21 forgotten propulsion blueprints, and it is a story that challenges everything we think we know about progress. We often imagine technological advancement as a straight line, a steady march forward where each new discovery builds neatly upon the last. But the truth is far more fascinating and far less orderly. History is littered with ideas that were simply too brilliant for their own time, concepts that arrived before the materials, the mathematics, or the mindset existed to bring them to life. Why were these revolutionary propulsion systems abandoned? Was it a lack of funding, the shadow of war, or perhaps the simple, stubborn weight of scientific dogma? The answers are as complex as the machines themselves, and they reveal a crucial lesson. Genius is not always recognized in its own era. Today, modern science, armed with supercomputers, nanotechnology, and a renewed sense of cosmic ambition, is finally catching up to the genius of the past, reopening these dusty files with a mixture of awe and revelation. So, this journey we are about to take together is more than a historical tour. It is an active investigation into potential futures that were once imagined, then lost. We will meet the visionary inventors who dared to dream of gravity control and faster-than-light travel, often at the cost of their reputations. We will examine the incredible machines they conceived, from reactionless drives that seem to defy physics to hyperdrives rooted in the deepest mysteries of the universe. This exploration is not just about satisfying curiosity. It is about unlocking a vault of possibilities that could redefine our place in the cosmos. The implications are staggering, suggesting that the path to the stars may have been mapped out long ago, waiting only for us to rediscover it. So, prepare to have your understanding of science and innovation turned upside down, as we begin by understanding the unique era that both created and condemned these magnificent ideas. To truly grasp the significance of these lost blueprints, we must first step back into the world that created them. Think of the period spanning from the late 1800s to the early 1900s. It was an age of steam and steel, of crackling electrical experiments, and bold new theories about the nature of reality. The air itself seemed charged with possibility. Inventors like Nikola Tesla were demonstrating seemingly magical feats of electricity, while physicists like Albert Einstein were rewriting the fundamental rules of the universe with theories of relativity. This was a time of unparalleled mechanical ingenuity, a golden age where individuals working in small workshops dared to challenge the established order of science. It was in this fertile ground of optimism and raw intellectual courage that the seeds of advanced propulsion were first planted. Yet, for every brilliant idea that saw the light of day, countless others were consigned to the shadows. The very spirit of exploration that fueled these concepts often became their undoing. Many of these propulsion blueprints were born from a desire to reach beyond our world, but they collided with the harsh realities of their time. The materials needed to build them, advanced alloys, temperature-resistant ceramics, or pure superconductors, simply did not exist. The complex mathematics required to prove their feasibility overwhelmed the calculating power of slide rules and human computers. A blueprint might be theoretically sound, even visionary, but if the technology to fabricate it was a century away, it was deemed impossible. These ideas were orphans of their time, born too early to survive. Compounding these technical hurdles were the immense social and political upheavals of the era. 2 world wars redirected scientific research almost exclusively toward immediate military applications. Funding for speculative, long-term projects like interstellar travel evaporated overnight as resources were poured into building tanks, aircraft, and eventually atomic bombs. A brilliant idea for a reactionless drive held little appeal for generals who needed more powerful rockets to deliver payloads across continents. Furthermore, the scientific establishment itself often acted as a gatekeeper. The prevailing dogma of the day, heavily influenced by Newtonian mechanics, was deeply resistant to concepts that seemed to challenge core principles. Inventors proposing gravity control or energy from the vacuum devices were frequently labeled cranks and dismissed without a fair hearing, their reputations ruined and their work ignored. This created a critical gap between theoretical physics and practical engineering. A mathematician might scribble a beautiful equation suggesting a way to manipulate space-time, but the engineer tasked with building it would throw up their hands in despair. There was no bridge between the abstract world of theory and the gritty reality of the machine shop. This transition from a concept on paper to a working prototype was where most of these propulsion dreams faltered. Without the advanced simulation software we have today, testing these ideas was prohibitively expensive and dangerous, leading many promising blueprints to be shelved as simply too risky to pursue. Understanding this context is not just a history lesson, it is the key to appreciating the rediscovery happening right now. It shows us that progress is not a straight, predictable line. It zigs and zags, doubles back on itself, and sometimes leaps forward by looking backward. A concept deemed nonsense in 1920 might be perfectly plausible in 2024, not because the laws of physics have changed, but because our tools for understanding and manipulating those laws have evolved beyond recognition. This cyclical nature of innovation, where old ideas are revisited with new eyes, sets the stage for our first incredible blueprint, a device that claimed to generate motion from nothing but spinning gyroscopes, a concept that modern science is only now beginning to take seriously. Now imagine a machine that seems to break one of the most fundamental rules of the universe, a device sitting on a laboratory bench, humming with energy, its internal parts spinning at tremendous speeds. And then, without expelling any fuel, without pushing against anything in the room, it begins to move. It slides forward, seemingly propelled by an invisible force. This was the audacious claim of the gyroscopic inertial drive, our first forgotten blueprint, and it presented a direct challenge to Isaac Newton's third law of motion, the principle that for every action, there must be an equal and opposite reaction. For conventional rockets, that reaction is the violent expulsion of hot gas. But this device promised motion from motion alone, a concept so revolutionary it was almost universally dismissed as impossible. The central figure in this early 20th century mystery was an inventor named John Worrell Keely. He claimed to have discovered a new physical force, which he called etheric force, and built intricate machines he called liberators that were filled with an array of carefully balanced and rapidly spinning gyroscopes. Keely's devices were marvels of mechanical complexity, with resonating tuning forks, vibrating strings, and those crucial spinning rotors all working in a delicate harmony. The proposed theory was that by precisely controlling the precession of these gyroscopes, that is, the slow, wobbling rotation of a spinning object's axis, he could create a net force in a single direction. Think of it like this: if you've ever held a spinning bicycle wheel and tried to tilt it, you've felt it fight back, twisting in your hands with a surprising force. Keely's blueprint attempted to harness and direct that twisting, gyroscopic force in a continuous cycle to produce a genuine, propellantless thrust. To the physicists of his day, this was not just wrong, it was heresy. The scientific establishment swiftly labeled Keely a fraud and his machine a perpetual motion device, an impossibility according to the cherished laws of thermodynamics. They argued that any force generated inside a closed system would simply cancel itself out. The gyroscopes might push against each other, creating internal stresses, but the machine as a whole could not propel itself forward without pushing on something external. Without any reproducible evidence that could be verified by skeptical observers, and with Keely's own explanations often veering into obscure and unprovable metaphysical concepts, the gyroscopic inertial drive was relegated to the fringes of science, a curious footnote in the history of failed inventions. For nearly a century, that's where the idea remained, gathering dust. But then, something remarkable happened. In the late 1990s and early 2000s, a new controversy erupted within the aerospace community with the emergence of the M-Drive. This device, a tapered microwave cavity, also claimed to produce thrust without expelling propellant. While the physics of the M-Drive is entirely different, its apparent violation of Newton's third law created a crisis of conscience for modern science. It forced researchers to ask a humbling question: were there subtle, overlooked phenomena within known physics that could indeed produce a net thrust? This renewed controversy became the key that unlocked the old filing cabinet. Scientists began to re-examine those old, discredited ideas with fresh eyes, and the principles of the gyroscopic inertial drive were suddenly back on the table. Modern researchers are now using advanced computer modeling and precision instrumentation to revisit the mathematics of gyroscopic precession. They are asking if, under very specific conditions of high-frequency oscillation and complex feedback loops, a system could indeed generate a tiny but measurable unidirectional force. The goal is no longer a machine that defies physics, but rather one that exploits its deepest, most subtle corners, the potential application micro-thrusters for satellites. In the frictionless environment of space, even the faintest whisper of continuous thrust is incredibly valuable. A satellite equipped with such a device could make minute adjustments to its orbit without ever running out of propellant, extending its operational life for decades. This modern reinterpretation doesn't promise to overthrow Newton, but to find a clever, previously unnoticed loophole within his laws, proving that even our most fundamental assumptions are worth challenging. This re-examination of inertia itself naturally leads us to a concept that goes a step further, attempting to manipulate not just motion, but the very force that governs it, gravity. Just a few years after the gyroscopic drive faded into obscurity, another equally baffling phenomenon emerged from a most unexpected place: a high-voltage laboratory. Picture a young physics student named Thomas Townsend Brown in the 1920s, meticulously experimenting with a type of electrical component called a Coolidge tube, an early kind of X-ray tube. While it was powered by a massive voltage source, he noticed something that should not have been possible. The entire tube, a heavy piece of equipment, seemed to exhibit a faint but distinct tendency to move toward its positive electrode whenever the power was switched on. It was as if the electrical charge itself was creating a tiny yet undeniable push. Brown, fascinated, refined his experiments, moving from X-ray tubes to simpler, more robust devices known as capacitors, components that store electrical charge. He found that when he charged a heavy, asymmetrical capacitor to a very high voltage, something remarkable happened. The capacitor would lose a minuscule amount of its weight, and if suspended like a pendulum, it would swing toward its positive pole. He called this the Biefeld-Brown Effect, naming it after his mentor, and it suggested a link that mainstream physics had long dismissed, a connection between electricity and gravity. The principle behind this effect is as elegant as it is controversial. A standard capacitor consists of two metal plates separated by an insulating material called a dielectric. Brown's key innovation was to make the capacitor asymmetrical, with one electrode being much larger than the other, or one being a sharp point and the other a flat plate. When an immense voltage, often in the tens or hundreds of thousands of volts, is applied, the theory proposes that the electrical stress on the dielectric material between the electrodes becomes unbalanced. This asymmetry, according to Brown's hypothesis, creates a net force that pushes the entire capacitor toward the positive side. He believed this was not merely an electrical phenomenon, but an electrogravitic one, that the high voltage field was somehow interacting with the gravitational field, producing a true propellantless thrust. Imagine the implications: a spacecraft that could generate thrust simply by applying electricity to a carefully shaped piece of metal and ceramic, with no need for bulky fuel tanks or roaring engines. Driven by this vision, Thomas Townsend Brown dedicated his life to exploring this effect. He progressed from small laboratory models to much larger devices, which he called gravitators. In the 1950s and 60s, he conducted demonstrations that stunned observers: disc-shaped gravitators, tethered to a central pole and charged with high voltage, would silently rotate around that pole. He even claimed to have built larger, manned prototypes that could generate enough lift to potentially influence the flight of an aircraft. His work attracted attention from the military, leading to secretive projects with names like Project Winterhaven, which aimed to develop electrogravitic fighters and bombers. Brown's ultimate dream was a disc-shaped craft that used this principle for both lift and propulsion, a concept that sounded eerily similar to the unidentified flying objects that were capturing the public's imagination at the time. However, this association with flying saucers, combined with a lack of a widely accepted theoretical explanation from established physics, ultimately led to his work being marginalized. The scientific mainstream remained deeply skeptical, offering a much more conventional explanation for what everyone was seeing. That conventional explanation is known as ionic wind or electrohydrodynamic thrust. Critics argued that Brown's effect had nothing to do with gravity. Instead, they proposed that the intense electric field at the smaller, sharper electrode was ionizing the air molecules around it, stripping electrons away and creating a cloud of positively charged ions. These ions would then be repelled violently toward the larger, negatively charged electrode. As they sped away, they would collide with neutral air molecules, transferring momentum and creating a flow of air, a wind, that pushed against the capacitor and caused the observed motion. It was a perfectly reasonable explanation based on well-understood physics, and it worked perfectly well in atmospheric conditions. For decades, this ionic wind theory was the official nail in the coffin for electrogravitics, dismissing Brown's life's work as a simple misunderstanding of a known, if dramatic, aerodynamic effect. But the story did not end there. A critical question remained: what would happen in a vacuum where there is no air to ionize? If the Biefeld-Brown effect was purely ionic wind, it should produce zero thrust in the emptiness of space. Intriguingly, some experimenters who repeated Brown's work inside vacuum chambers reported that a small, residual thrust seemed to persist even after all the air was pumped out. This was the spark that ignited modern rediscovery. Today, researchers at NASA Eagleworks Laboratory, as well as in various universities and private aerospace companies, are conducting highly precise experiments using sensitive torsion balances and vacuum chambers to settle the debate once and for all. They are testing advanced dielectric materials that can withstand colossal electric fields and using modern power supplies to generate voltages that Brown could only have dreamed of. The goal is to isolate and measure any thrust that cannot be attributed to ionic effects. The implications of confirming a genuine, non-ionic Biefeld-Brown effect are profound. It would suggest that our understanding of gravity and its relationship with electromagnetism is fundamentally incomplete. It could open the door to propulsion systems of incredible efficiency. A satellite could maneuver for years using only solar power, its thrusters consisting of nothing more than solid-state capacitors. For deep space missions, such a technology could enable constant, low-thrust acceleration that would gradually build up to tremendous speeds, making journeys to the outer planets and beyond far more feasible. Whether the effect is a novel form of thrust or an exotic manifestation of ionic phenomena, its study is pushing the boundaries of materials science and plasma physics. This tantalizing bridge between the force that holds our feet to the ground and the force that lights our cities leads us directly to an even more ambitious concept, a device that claimed not just to manipulate gravity, but to defy it entirely through the power of magnets. While Thomas Townsend Brown was exploring the link between high voltage and gravity, a different kind of visionary on the other side of the world was building a machine that promised to achieve the same goal with an entirely different principle: the raw power of magnets. Our next blueprint takes us to 1950s England, where an electrical engineer named John Searl claimed to have constructed a device so revolutionary it not only generated its own electricity but also defied gravity itself. He called it the Searl Effect Generator, or SEG, and its proposed mechanism was a symphony of spinning magnets and rolling cylinders that, if his accounts are to be believed, literally lifted off the ground and flew. The design of the Searl Effect Generator was as intricate as it was audacious. Searl's blueprint called for a large, stationary outer ring, which was itself a complex composite magnet. Inside this ring, a series of smaller cylindrical rollers, also magnetized, were set to move. These weren't just ordinary magnets, however. Searl insisted that each component had to be built using a specific, layered combination of metals, often including neodymium, iron, and nylon, which he claimed created a unique interaction when in motion. The rollers would be positioned around a central core, and the entire assembly was designed so that once the rollers were set spinning, they would be propelled around the track of the outer ring by magnetic forces. This is where the claimed magic began. According to Searl, as the rollers gained speed, they would induce powerful electrical currents in the surrounding air, creating a phenomenon called the Searl effect. This effect, he said, would cause the device to generate a negative ion cloud around it, effectively reducing its weight. At a certain critical rotational speed, the SEG would supposedly become weightless, levitate, and if untethered, accelerate upwards into the sky, powered by its own self-sustaining magnetic interaction. To the scientific establishment of the day, this was not just improbable, it was an outright affront to fundamental physics. The claims of self-sustaining rotation and over-unity energy generation producing more energy than was put in directly violated the law of conservation of energy, a cornerstone of classical physics. Furthermore, Searle's descriptions of the effect were often couched in his own unique terminology and theories that did not align with mainstream electromagnetic theory. When he and his team claimed to have lost a full-scale, manned version of the craft during a test flight, the story only fueled skepticism. The scientific community demanded one thing above all else: reproducible evidence. Despite Searle's passionate assertions and his display of smaller, tabletop models that he said demonstrated the principle, no independent researcher was ever able to build a working SEG that performed as advertised. Without verifiable proof, and with its core principles seemingly breaking immutable physical laws, the Searle effect generator was dismissed as an elaborate hoax or the product of a fervent imagination, joining the ranks of other perpetual motion machines confined to the fringes of science. For decades, the SEG remained a curious footnote, a story for enthusiasts of alternative science. But much like our previous blueprints, time has a way of changing perspectives. The modern rediscovery of Searle's ideas isn't about accepting his original claims at face value, but rather about re-examining the underlying physical phenomena he might have been observing, even if he misinterpreted them. Today, physicists are looking at the SEG blueprint through the lens of advanced magnetic interactions that simply weren't well understood in the 1950s. For instance, the precise arrangement of alternating magnetic fields in a rotating system could potentially create complex, non-linear effects. Researchers are asking if Searle might have inadvertently stumbled upon a way to manipulate magnetic domains or induce unusual electromagnetic resonances that could produce measurable, if subtle, forces. The most compelling connection to modern physics lies in the realm of superconductivity and magnetic levitation. When a superconductor is cooled below its critical temperature, it expels magnetic fields in a phenomenon known as the Meissner effect, allowing it to levitate effortlessly above a magnet. While the SEG did not use superconductors, the concept of using magnetic fields to achieve stable levitation is no longer science fiction. It's the principle behind maglev trains. Some researchers speculate that the specific layered materials Searle described might, under the right conditions of motion and magnetic flux, exhibit properties analogous to a type of magnetic bearing or even create localized areas of diamagnetic repulsion. The idea isn't that the SEG violated physics, but that it might have been a crude, mechanical attempt to harness very real and very powerful magnetic phenomena that we are only now beginning to master with modern materials science. This re-evaluation shifts the narrative from one of fraud to one of a misunderstood pioneer, a man who saw a glimpse of a magnetic future but lacked the tools and the language to prove it to a skeptical world. This profound idea of manipulating fundamental forces to overcome gravity serves as a perfect prelude to a concept that goes even deeper, aiming to engineer the very geometry of spacetime. From the tangible world of spinning magnets and high-voltage capacitors, we now venture into the most abstract and mathematically profound of our forgotten blueprints. To understand this next concept, you must first picture its creator, Burkhard Heim, a German physicist whose life story is as extraordinary as his theories. A horrific laboratory accident during World War II left Heim blind and without hands, confining him to a world of pure thought. Yet, from this isolation, he constructed one of the most ambitious intellectual edifices of the 20th century, a unified field theory that sought to weave together gravity, electromagnetism, and quantum mechanics into a single, elegant tapestry. It was within this complex mathematical framework that Heim found the blueprint for a propulsion system so revolutionary it bordered on magic, a hyperdrive. Heim's theory proposed a universe with more than the four dimensions we experience. Beyond length, width, height, and time, he postulated the existence of two additional dimensions, which he called X5 and X6. In this six-dimensional reality, Heim's equations suggested a breathtaking possibility that electromagnetic energy could be directly converted into gravitational fields. Imagine a spacecraft equipped with a device that could transform the power from its reactor or a captured beam of light not into heat or motion, but into a localized gravitational field. By carefully controlling the polarity and strength of this manufactured gravity, the ship could effectively push against the fabric of spacetime itself. It wouldn't propel itself like a rocket pushing against expelled fuel. Instead, it would create a slope in spacetime and slide down it, a process Heim called gravitophoton field propulsion. This field propulsion would envelop the craft in a protective bubble, insulating it from the effects of acceleration and, most astonishingly, allowing for faster-than-light travel without the punishing time dilation predicted by Einstein's theory of relativity. Passengers could travel to a star 100 light-years away and back, arriving home only a few years older, not centuries. The reason this monumental blueprint was shelved and largely ignored for decades boils down to one primary obstacle: the sheer, impenetrable complexity of its mathematics. Heim's work was not written in the language of conventional physics that most researchers were fluent in. He developed his own unique mathematical formalism, a dense forest of symbols and operators that even seasoned theoretical physicists found extraordinarily difficult to navigate. Without the ability to easily translate his ideas into testable predictions or reconcile them with the standard model of particle physics, the mainstream scientific community treated Heim theory with a mixture of skepticism and polite indifference. It was a castle built in the air, beautiful in its ambition but seemingly unconnected to the solid ground of experimental verification. For a discipline that advances through peer review and reproducible results, Heim's isolated genius remained an intriguing but ultimately inaccessible cul-de-sac. The story of its rediscovery, however, is a testament to the power of persistence. Decades after Heim published his work, a pair of physicists, Walter Dröscher and Joachim Heuser, took up the challenge. They dedicated years to deciphering and extending Heim's original equations, publishing papers that outlined a concrete concept for a field propulsion engine based on the theory. Their work proposed a device that would use rapidly rotating magnetic fields, generated by a superconductor, to excite the quantum vacuum and produce the gravitophoton forces Heim had predicted. This was no longer just abstract math, it was a theoretical engineering blueprint. This caught the attention of a small, advanced concepts group within NASA known as the Eagleworks Laboratory. In the mid-2000s, there were brief but serious discussions about the potential implications of Heim theory for breakthrough propulsion. The interest was cautious, born of a desire to leave no stone unturned in the search for revolutionary spaceflight technologies, but it signaled a profound shift. An idea once confined to the absolute fringes was being given a hearing at the highest levels of aerospace research. This modern reevaluation doesn't mean the Heim drive is a proven reality. The mathematics remains formidable, and the energy requirements for generating a measurable effect are still far beyond our current capabilities. The real significance lies in the door it has reopened. Heim theory represents a fundamentally different approach to the problem of propulsion, one that seeks to master gravity itself rather than brute force our way through space with chemical explosions. It challenges us to think of spacetime not as a static stage, but as a dynamic medium that can be shaped and manipulated. This leap from tangible machinery to the theoretical engineering of reality itself is perhaps the greatest legacy of Burkhard Heim's forgotten blueprint. And it is this very contrast that makes our next concept so compelling: as we return from the rarefied heights of theoretical physics to the visceral, thunderous world of controlled explosions. After exploring the mind-bending theoretical realms of gravity control and hyperdrives, we now return to the tangible, audible world of engineering with a concept that is as visceral as it is clever. This is the story of the pulsed plasma jet propulsion system, a blueprint born not from abstract equations but from the practical need to nudge satellites with exquisite precision. Imagine the early days of the space race. The world was captivated by the thunderous roar of massive chemical rockets, giants that hurled capsules into orbit with raw, explosive power. But once a satellite was silently coasting hundreds of miles above the Earth, a new challenge emerged: how to make tiny, delicate adjustments to its position or orientation. Firing a large chemical thruster for such a task would be like using a sledgehammer to perform watchmaking. It was far too crude and wasteful. Engineers needed a scalpel, and the pulsed plasma thruster promised to be exactly that. The fundamental principle is both simple and brilliant. Instead of a continuous fuel-guzzling burn, this system operates in rapid, discrete pulses. The blueprint calls for a small chamber containing a solid material, typically a block of a special plastic called Teflon. Behind this block are two electrodes. When a powerful burst of electricity is discharged across these electrodes, it creates an intense electric arc, similar to a miniature bolt of lightning. This arc strikes the surface of the Teflon, instantly superheating it and ablating or vaporizing a tiny, controlled amount of material. The vaporized Teflon is transformed into a fourth state of matter, plasma, a seething soup of ions and electrons. This plasma, now fiercely hot and electrically conductive, is then accelerated out of the chamber by the same electromagnetic forces that created it, shooting through a nozzle to produce a brief, high-velocity jet of thrust. The entire cycle, charging, arcing, ablating, and accelerating, takes just milliseconds, and it can be repeated thousands of times per second, creating a steady, controllable push from a relentless series of microscopic explosions. The advantages of this pulsed approach were immediately apparent to spaceflight pioneers in the 1960s. First and foremost is its incredible precision. Because each pulse delivers a minuscule, quantifiable amount of thrust, a satellite's computer can control its attitude or pointing direction with an accuracy measured in fractions of a degree. This is absolutely vital for telescopes that need to remain perfectly still while observing distant galaxies, or for communication satellites that must keep their antennas locked on a specific spot on Earth. Secondly, the system is mechanically simple. It has very few moving parts, no complex pumps or valves, making it inherently reliable in the harsh environment of space. And because it uses a solid propellant, there are no sloshing liquids or high-pressure gas tanks to manage, which simplifies the spacecraft's design and improves its safety. For the specialized role of satellite station keeping and orientation, the pulsed plasma thruster seemed like an ideal solution. So why did this promising blueprint end up in the forgotten files? The answer lies in two stubborn technical hurdles that the materials science of the day could not overcome. The first and most critical problem was electrode erosion. Each time that powerful electric arc fired, it would literally blast microscopic pieces of the metal electrodes away. Over thousands and then millions of pulses, the electrodes would gradually wear down, changing the characteristics of the arc and eventually leading to the thruster's failure. It was a death by 1,000 cuts, and for long-duration missions, this limited lifespan was a deal-breaker. The second major issue was low overall thrust. While the efficiency or specific impulse of these thrusters was good, the absolute pushing power was undeniably weak. A typical pulsed plasma thruster might produce a force comparable to the weight of a single sheet of paper resting on your hand. This made it useless for major maneuvers like changing orbits, relegating it to a niche role that, at the time, seemed insufficient to justify further development. With the space race focused on bigger rockets and grander missions, the delicate pulsed plasma thruster was sidelined in favor of more powerful, though less precise, propulsion technologies. For decades, it remained a specialist tool, a curiosity. But then, a revolution began, not in propulsion theory, but in materials science. The modern rediscovery of this blueprint is a direct result of our newfound ability to engineer matter at an incredibly fine scale. The problem of electrode erosion, once thought intractable, is now being solved by advanced ceramics. Materials like boron nitride and mica are incredibly hard, resistant to extreme heat, and are poor electrical conductors, making them ideal for lining the thruster chamber and protecting components from the punishing plasma arc. Furthermore, research into superconductors has yielded new alloys for the electrodes themselves that can withstand far greater thermal and electrical stress without degrading. These material advances have dramatically extended the operational life of pulsed plasma thrusters from millions to billions of pulses, making them viable for missions lasting many years. This resurgence is perfectly timed for the new space age, dominated by small satellites and CubeSats. For these miniature spacecraft, every gram of weight and every cubic centimeter of volume is precious. The pulsed plasma thruster is an almost perfect fit. It is compact, lightweight, and requires no complex plumbing. Companies and universities around the world are now developing miniature versions of these thrusters to provide attitude control and drag compensation for constellations of small satellites in low Earth orbit. Modern electronics allow for incredibly precise control over the timing and power of each pulse, turning what was once a simple on-off switch into a finely tuned instrument. The blueprint didn't change, but the world finally developed the tools to build it properly. It's a clear and satisfying case of an idea that was simply waiting for its moment, proving that sometimes progress in one field can unlock the potential of a forgotten technology in another. This elegant, efficient use of plasma serves as a perfect prelude to a system that employs the same state of matter in a manner that is anything but subtle. If the pulsed plasma thruster represents the delicate art of spaceflight precision, then our next forgotten blueprint is its absolute antithesis, a concept of such raw, unadulterated power that it borders on the apocalyptic. We are about to enter the realm of the nuclear saltwater rocket, a propulsion system so audacious that it essentially involves building a continuous, uncontrolled nuclear explosion at the heart of your spacecraft and then riding the shockwave. The principle is as terrifying as it is brilliant. Imagine, instead of a traditional rocket fuel like liquid hydrogen and oxygen, your propellant tank is filled with a watery solution. But this is no ordinary water. Dissolved within it are highly enriched nuclear salts, compounds of elements like uranium-235 or plutonium-239, the very stuff of atomic bombs. This mixture is a liquid that is, for all intents and purposes, a critical mass in waiting. The blueprint for this radical engine is most famously championed in the modern era by the visionary aerospace engineer Robert Zubrin, but its conceptual roots dig much deeper into the fever dream speculation of the mid-20th century when scientists were first grappling with the immense power of the atom. The engine itself is deceptively simple in design. A heavily shielded tank holds this unstable, radioactive solution. When the rocket is ready to fire, pumps force the solution into a reaction chamber, which is lined with a neutron-absorbing material. As the concentration of nuclear salt in the chamber increases, it reaches a point of criticality. The atoms of uranium or plutonium begin to split in a self-sustaining chain reaction of nuclear fission. But here's the crucial difference from a nuclear reactor. There is no control. There are no control rods to moderate the reaction. Instead, the design relies on the continuous flow of the liquid itself. As the nuclear salt water is injected into the chamber, it undergoes a furious fission reaction, and the resulting superheated plasma, a mixture of steam and fission products at temperatures exceeding the surface of the sun, is blasted out of a nozzle at tremendous velocity, generating colossal thrust. The engine doesn't burn fuel, it continuously detonates it. The performance figures for such a device are almost incomprehensible when compared to the chemical rockets we use today. The key metric for rocket efficiency is called specific impulse, which is essentially a measure of how much push you get for every pound of propellant. A good chemical rocket, like the one that powered the Saturn V to the moon, might have a specific impulse of around 450 seconds. The nuclear salt water rocket, by contrast, could achieve a specific impulse of 6,000, 7,000, or even higher. This isn't just a minor improvement, it's a quantum leap. A spacecraft powered by this engine could accelerate at a steady rate for weeks or months, enabling transit times to Mars measured in weeks instead of months, and journeys to the outer planets like Jupiter and Saturn in a matter of months rather than years. It would utterly shatter the tyranny of the rocket equation that has constrained human spaceflight since its inception, opening the entire solar system to rapid, large-scale exploration. So why was this incredible blueprint, with its promise of the stars, locked away and forgotten? The reasons are as powerful as the engine itself, rooted in the political and technological realities of the Cold War. The first and most obvious problem is safety, or rather, the terrifying lack of it. A vehicle powered by a nuclear saltwater rocket would be, by its very nature, a mobile environmental catastrophe waiting to happen. A launch failure would not simply be an explosion. It would be a dirty bomb of unimaginable scale, scattering highly radioactive fissile material across a wide area. The mere thought of launching such a device from the Earth's surface was politically untenable, a non-starter for any government. Furthermore, containing the reaction itself presented material science challenges that were far beyond the capabilities of the 1960s and 70s. The reaction chamber would be subjected to a hellish combination of extreme neutron flux, intense heat, and corrosive fission products that would vaporize any known material in seconds. The engineering required to contain a continuous nuclear fire was at the time a fantasy. For decades, the nuclear saltwater rocket remained the ultimate what-if concept, a symbol of a path not taken due to its inherent dangers. But today, the context is shifting dramatically, leading to a serious re-evaluation of this forgotten blueprint. The rise of advanced robotics and remote operation means that such a spacecraft would likely never be crewed during its initial acceleration phase. It could be assembled and fueled in high Earth orbit or at a Lagrange point, far from human populations, and controlled remotely for its journey across the solar system. This eliminates the primary political and safety objection of an Earth-based launch. Even more critically, the field of materials science has advanced in leaps and bounds. Research into advanced ceramics, carbon-carbon composites, and novel metal alloys developed for fusion reactors has given us materials that can withstand temperatures and radiation levels that would have been unthinkable half a century ago. While the challenge of building a durable reaction chamber remains immense, it is no longer considered physically impossible. For ambitious interstellar precursor missions, such as a probe to 1,000 astronomical units or a fast flyby of a distant dwarf planet like Sedna, the nuclear saltwater rocket offers a level of performance that no other near-term technology can match. It represents a willingness to embrace controlled, monumental risk in pursuit of a monumental reward, a philosophy that is gaining traction as we set our sights beyond the moon. This vision of harnessing a star's worth of power onboard a spacecraft stands in stark contrast to our next concept, which seeks to achieve motion not through brute force, but by quietly drawing energy from the empty space that surrounds it. Now, let us shift our focus from the raw, explosive power of nuclear fission to a concept of propulsion that is almost its polar opposite, a technology of profound silence and elegant simplicity. Imagine a spacecraft that doesn't roar, doesn't vibrate, and carries no fuel. It simply moves, gliding through the void as if pushed by an invisible hand. This is the promise of ambient temperature superconductor propulsion, a blueprint that has tantalized physicists and engineers for generations, not because of its complexity, but because of its breathtaking potential for efficiency. The entire concept hinges on a single, monumental discovery, a material that can superconduct electricity, offering zero resistance to electrical current, not at the frigid temperatures of liquid nitrogen or helium, but at the comfortable, everyday temperatures of a room here on Earth. The theoretical foundation for this idea is remarkably straightforward, rooted in principles we already understand. We know that a moving electric charge creates a magnetic field. We also know from Faraday's law of induction that a changing magnetic field can induce an electric current. Now, imagine a loop made of this miraculous room temperature superconducting material. Once an electrical current is started in this loop, it would flow forever without any loss of energy, creating a permanent, incredibly powerful magnetic field. This is the famous property of superconductors known as persistent current. A spacecraft equipped with such a loop could, in theory, use this stable magnetic field to interact with other magnetic fields found naturally in space. The most obvious example is the magnetic field of a planet. Just as two magnets can push or pull on each other, the superconducting magnet on the spacecraft could repel itself against a planet's magnetic field, generating lift or thrust without expelling a single molecule of propellant. This concept, often called a magnetic sail or mag-sail, would be the ultimate in efficiency, using the free, omnipresent energy of celestial magnetic fields for propulsion. Early visionaries, dreaming of this possibility throughout the 20th century, sketched out blueprints for vehicles that could use this principle not just for propulsion, but for levitation right here on Earth. Imagine a train that floats silently above its track, not on a cushion of air, but on an invisible magnetic force, accelerated to incredible speeds with minimal energy input. This is, of course, the principle behind maglev trains we have today, but current maglev technology requires complex and expensive cooling systems to keep the superconductors at their ultra-cold operating temperatures. The dream was always to achieve this without the cryogenics, to have a material that could perform this feat at ambient conditions. Such a material would revolutionize not just transportation on Earth, but open the solar system. A satellite could adjust its orbit indefinitely. A probe could travel to Jupiter, using the gas giant's immense magnetic field as a brake or an accelerator, sailing on magnetic fields as surely as an ancient ship sailed on the wind. For over a century, however, this blueprint remained firmly in the realm of science fiction for one simple, frustrating reason: the material itself did not exist. The hunt for a room temperature superconductor became one of the holy grails of condensed matter physics. For decades, progress was incremental. Scientists discovered materials that superconducted, but only when cooled to temperatures close to absolute zero, around -450 degrees Fahrenheit, requiring bulky and delicate systems of liquid helium. Later, in the 1980s, a new class of materials known as high-temperature superconductors was discovered, which could operate at the warmer but still cryogenic temperature of liquid nitrogen, around -320 degrees Fahrenheit. This was a massive leap forward, making superconductivity more practical, but it was still a far cry from the dream of a material that worked in the environment of a spacecraft or a passenger vehicle. The propulsion blueprint was elegant and sound, but it was a key waiting for a lock that had not yet been forged. The scientific consensus for a long time was that ambient temperature superconductivity might even be physically impossible, a theoretical dead end. The turning point, the event that pulled this blueprint out of the forgotten files and into the glare of modern laboratories, began in the last decade with a series of startling breakthroughs. Researchers started experimenting with a completely different approach, squeezing materials under immense pressure. The idea was that extreme pressure could force atoms closer together, altering their electronic structure in ways that might enable superconductivity at higher temperatures. The results were astonishing. In 2020, a team announced they had observed superconductivity in a compound of carbon, sulfur, and hydrogen, but only when it was compressed between two diamonds to a pressure exceeding 2.5 million times Earth's atmospheric pressure. While this was not a practical material for building a spacecraft magnet, it was a monumental proof of principle. It demonstrated that superconductivity could, in fact, occur at room temperature. The dam of impossibility had been breached. This discovery ignited a firestorm of research into other hydride compounds and novel materials like layered graphene structures. Scientists are now exploring ways to achieve the same superconducting state through chemical engineering, rather than physical pressure trying to create a material that is intrinsically pre-stressed at the atomic level. Every few months, new papers are published claiming advances in understanding or new candidate materials that bring us closer to the dream. This ongoing revolution has completely revitalized the old propulsion concepts. Aerospace engineers who once dismissed magnetic sails as a far future fantasy are now actively running new simulations and drafting updated blueprints, factoring in the potential properties of these nascent materials. The conversation has shifted from if to when, and the implications are staggering. A propulsion system based on this technology would be virtually silent, require no refueling, and have an operational lifetime limited only by the durability of the spacecraft's other components. It represents a clean, sustainable, and incredibly efficient pathway to the stars, a concept that has been waiting in the wings for a century and is finally hearing its cue. This vision of effortless, silent motion through the manipulation of fundamental forces finds a fascinating parallel in our next blueprint, which proposes to achieve a similar goal using the pure, massless power of light itself. But if sailing on magnetic fields represents a form of cosmic sailing, then our next concept takes this idea of sailing to its most fundamental extreme. Imagine a vessel that needs no fuel, no nuclear reactor, not even a superconducting magnet. Instead, it is pushed forward by the gentle yet relentless pressure of light itself. This is the core idea behind the photonic laser thruster, or PLT, a blueprint that transforms the most ephemeral thing in the universe, a beam of photons, into a practical source of propulsion. While the concept of a solar sail, which uses sunlight for a push, has been around for a long time, the photonic laser thruster is a far more sophisticated and powerful evolution of that principle. It doesn't just passively catch the light from the sun, it actively creates and amplifies its own perfectly focused beam of light to generate thrust. The elegance of the PLT lies in its clever use of optical resonance. The basic blueprint involves two key components: a powerful laser and a pair of highly reflective mirrors, one on the spacecraft and one on a stationary base, perhaps on Earth or in orbit. The laser is fired from the base station towards the spacecraft, where it strikes its first mirror. But instead of simply bouncing off, the light is designed to enter the space between the two mirrors, which are precisely aligned to form what's called an optical cavity. Inside this cavity, the laser light bounces back and forth thousands or even millions of times, reflecting between the two mirrors. With each reflection, the light transfers a tiny amount of momentum to the mirrors. This is a well-understood principle of physics. Light, despite having no mass, carries momentum. When a photon strikes a surface and reflects, it gives that surface a minuscule push. Normally, this push is so small it's negligible, but the photonic laser thruster's genius is in amplification through repetition. By trapping the light and making it bounce countless times, the system multiplies that tiny push by a huge factor, creating a significant and continuous thrust on the spacecraft's mirror, pushing it away from the source. This method of momentum transfer offers a pathway to speeds that are simply unattainable with any kind of fuel-based rocket. Because the photons themselves are massless, the spacecraft isn't constrained by the rocket equation, the tyrannical rule that requires exponentially more propellant to carry even a little more propellant. The PLT's thrust can, in theory, be maintained for years, even decades, as long as the base station can keep the laser powered and accurately aimed. This constant, low-thrust acceleration would gradually build up to astonishing velocities, potentially reaching a significant fraction of the speed of light over interstellar distances. It becomes a true starship engine, capable of propelling probes to nearby star systems within a human lifetime. The potential applications for rapid transit within our own solar system are equally revolutionary, turning journeys to Mars into affairs of weeks rather than months. So why did this brilliant blueprint, with its roots in the early days of laser research in the 1960s and 70s, end up gathering dust for so long? The challenges were not theoretical but intensely practical, and they were monumental. The first and most obvious hurdle was power. To generate even a modest amount of thrust for a meaningful spacecraft, the laser would need to be phenomenally powerful, requiring gigawatts of continuous energy, equivalent to the output of several large nuclear power plants. The infrastructure needed to generate and power such a laser was beyond contemplation. The second, even more delicate challenge was precision. Maintaining the optical cavity between two mirrors separated by thousands or millions of kilometers is an optical engineer's nightmare. The alignment must be perfect to within a fraction of a wavelength of light. Any tiny vibration, any slight drift in the spacecraft's attitude, or any distortion from the intervening atmosphere would cause the laser beam to miss the distant mirror, breaking the resonant cavity and instantly cutting off the thrust. For decades, these twin barriers of immense power and impossible precision made the PLT a fascinating thought experiment, but not a serious engineering proposal. The story of its rediscovery is a classic case of parallel progress in unrelated fields finally converging to make the impossible seem plausible. The revolution in laser technology has been breathtaking. The development of fiber lasers and phased array lasers has given us systems that are not only vastly more powerful, but also incredibly efficient and capable of being precisely combined to create a single, coherent beam of unprecedented intensity. At the same time, advances in adaptive optics, technology originally developed for large ground-based telescopes to correct for the blurring effects of Earth's atmosphere, now provide the tools to keep a laser beam perfectly locked onto a tiny target over astronomical distances. Perhaps the most crucial enabling technology has been the rise of photonic crystals and metamaterials. These are materials engineered at the nanoscale to control light in ways nature never intended. They can be used to create mirrors with near-perfect reflectivity, losing only one photon in a million, which would dramatically increase the efficiency of the resonant cavity. With these tools in hand, aerospace researchers are now running new simulations and designing small-scale laboratory prototypes to test the principles of the photonic laser thruster. The initial goal is not to send a probe to Alpha Centauri, but to demonstrate the technology for satellite station keeping in Earth orbit. A small CubeSat equipped with a mirror could be precisely maneuvered by a ground-based laser, proving the concept's viability. This incremental approach is turning science fiction into a credible roadmap for the future. The PLT represents a shift towards infrastructure-based spaceflight, where the propulsion system is partly divorced from the vehicle itself. It asks us to think big, to invest in large, permanent assets like powerful laser arrays that can serve entire fleets of spacecraft. This vision of using pure, amplified light to navigate the cosmos is a profound demonstration of our ability to harness the most fundamental forces, a theme that finds an even deeper resonance in our next blueprint, which ventures into the quantum realm to draw power from the very emptiness of space. After exploring the immense power of light, we now plunge into a realm where the very definition of nothing is turned on its head. To understand our next forgotten blueprint, you must first accept a deeply strange fact about the universe, confirmed by countless experiments. A perfect vacuum, a volume of space completely empty of all matter, is not truly empty. Instead, it is a seething, bubbling foam of energy. At the quantum scale, pairs of virtual particles and their antiparticles constantly flicker into and out of existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other and returning it. This ceaseless activity, known as quantum fluctuation, means that empty space is alive with a background energy, often called zero-point energy, and it was the Dutch physicist Hendrik Casimir who, in 1948, predicted a startlingly simple way to demonstrate this energy's reality. The Casimir effect is the phenomenon that brings these ghostly quantum fluctuations into the tangible world. Casimir calculated that if you take two perfectly smooth, uncharged metallic plates and place them incredibly close together in a vacuum, so close that the gap between them is narrower than the wavelength of most virtual particles, something remarkable happens. Outside the plates, the full spectrum of virtual particles can pop into existence, pushing on the plates from the outside. But inside the narrow gap, only particles with wavelengths smaller than the gap can appear. This creates a pressure imbalance, with more virtual particles pushing on the outside of the plates than on the inside. The net result is an invisible force that pushes the two plates together. It's not a force of magnetism or gravity. It is a direct manifestation of the energy of the vacuum itself. When this force was experimentally measured with great precision decades later, it provided stunning confirmation that the quantum vacuum is not passive. It exerts a real physical pressure. This discovery immediately sparked the imaginations of theoretical physicists and engineers. If the vacuum of space contains this boundless, omnipresent energy, could it be tapped for propulsion? The blueprint for a vacuum energy propulsion system began to take shape in the mid-20th century. The initial idea was breathtakingly ambitious: find a way to create a similar imbalance in pressure, not just between two plates, but around a single object to produce a net thrust in one direction. Imagine a spacecraft equipped with a device that could somehow shield one side of itself from the full pressure of the quantum vacuum, while leaving the other side exposed. The endless barrage of virtual particles on the unshielded side would push the craft forward, a ship sailing on the energy sea of spacetime itself. Such an engine would require no fuel tanks and no external power source. It would draw its propulsion from the very fabric of the universe. The immense challenge, and the primary reason this blueprint was filed away as a fringe idea for so long, is the problem of symmetry. The Casimir effect, as originally conceived, produces an attractive force that pulls plates together. It does not, on its own, create a directional push. To get a net thrust for propulsion, you would need to break this symmetry. You would need to engineer a situation where the Casimir force is stronger on one side of your vehicle than the other. For decades, this seemed like an insurmountable obstacle. The quantum vacuum is, by its nature, uniform and isotropic. It should exert the same pressure in all directions. Any attempt to create a propulsive force from it seemed analogous to trying to move a boat by blowing into your own sails. The forces would simply cancel out. Mainstream physics dismissed the concept as a perpetual motion machine in disguise, a violation of the conservation of momentum that was fundamentally impossible. The modern rediscovery of this audacious blueprint is a direct result of our newfound mastery over the world of the very small. The field of nanotechnology has given us the tools to engineer materials and structures at the nanometer scale, which is precisely the scale at which the Casimir force operates. Scientists are no longer limited to studying simple, parallel plates. They are now designing and fabricating complex, asymmetrical nanostructures. Think of a surface covered not in flat plates, but in an array of incredibly tiny, shaped pillars, grooves, or spirals. The geometry of these structures can influence how virtual particles interact with them. Recent theoretical work and early experiments suggest that an array of nanoscale fins or a specially corrugated surface could indeed experience a lateral or shearing Casimir force, a push not just inward but sideways. This is the critical breakthrough, the possibility of creating a net directional force not by trying to block the vacuum, but by cleverly shaping a surface to interact with it asymmetrically. This research is still in its earliest, most delicate stages, conducted in ultra-high vacuum chambers where displacements are measured in billionths of a meter. The forces involved are minuscule, far too small to propel a macroscopic object. Yet, the implications are profound. The first applications would likely be in the world of micro-electromechanical systems, or MEMS, tiny mechanical devices on a chip. A microscopic Casimir thruster could provide precise actuation for nanobots or optical switches without any electrical connections, powered solely by the ambient energy of the vacuum. But the long-term vision remains. If the effect can be understood, amplified, and scaled, it points toward a future of truly fuel-less propulsion. A spacecraft equipped with a hull engineered at the quantum level could, in theory, harness the infinite energy of empty space for a continuous, inexhaustible thrust. This journey into the heart of quantum weirdness, where emptiness itself becomes a source of power, beautifully sets the stage for a concept that is somehow even more fundamental, as we turn from the chaotic foam of the quantum world to the pristine, geometric order of a purely theoretical engine. From the ethereal realm of quantum fluctuations, we now return to the solid, tangible world of gears, weights, and mechanical vibration, with a device that remains one of the most stubborn and controversial puzzles in the history of propulsion. This is the story of the Dean Drive, a machine that, according to its inventor, could push itself forward using nothing but the clever orchestration of its own internal moving parts. In the 1950s, an American inventor named Norman L. Dean unveiled a device that looked to the untrained eye like a jumble of motors, cams, and eccentric weights mounted on a platform. But Dean claimed this mechanical assembly was anything but ordinary. He demonstrated it by placing the entire unit on a set of scales or letting it rest on a table. When he switched it on, the machine would reportedly vibrate intensely, yet instead of merely shaking in place as any normal unbalanced motor would, it would allegedly exhibit a net force in one direction, sliding across the surface as if being pushed by an invisible hand. The claim, once again, was reactionless thrust, a force generated without expelling any propellant, seemingly defying Newton's third law. The proposed blueprint of the Dean drive was centered on the principle of asymmetric mechanical oscillation. While the exact internal workings were a closely guarded secret, Dean's patents and descriptions suggest a system of weights that were driven in a very specific, non-reciprocal pattern. Imagine a simple back and forth vibration. In a symmetric system, the force of a weight moving to the left is perfectly cancelled out by the force of it moving to the right a moment later, resulting in no net movement. Dean's innovation was supposedly to break this symmetry. His drive allegedly created a situation where the impulses in one direction were somehow different, perhaps sharper, faster, or more forceful than the impulses in the opposite direction. Through a complex arrangement of cams and levers, the device might have generated a series of unequal jolts. The theory was that if you could make the push in one direction fundamentally different from the recoil in the other over many rapid cycles, these tiny imbalances could add up to a measurable unidirectional force. It was an attempt to coax a directed motion out of the chaotic energy of vibration itself. The demonstrations attracted a flurry of attention, including brief interest from the U.S. military and coverage in popular science magazines of the era. The allure was undeniable: a simple mechanical engine that needed only electricity to produce thrust, with no fiery exhaust or complex plumbing. However, this interest was short-lived. When physicists and engineers were invited to examine the device, they consistently failed to verify the reactionless thrust under controlled conditions. Skeptics proposed a much more conventional explanation. The effect was a subtle form of mechanical walking. They argued that the vibrations were simply causing the drive to interact with the surface it was resting on in an uneven way. For instance, on a table, the microscopic imperfections in the wood or the slight give of the legs could allow the vibrating machine to creep forward, much like a cell phone can slowly vibrate its way off a table. The true test would be in a frictionless environment or on a suspension system that isolated the drive from any external leverage. When such tests were proposed or attempted, the Dean drive reportedly failed to produce any thrust. The scientific consensus swiftly concluded it was an inadvertent illusion or a clever, if ultimately explainable, trick. Yet, the legend of the Dean drive never completely died. For decades, it has been a favorite topic among amateur inventors and proponents of alternative science, who argue that the mainstream tests were flawed or that the true secret of the drive was never properly understood. The possible explanations for a genuine effect, should one exist, range from the highly speculative to the revolutionary. One fringe theory suggests that the high-frequency oscillations might interact with the Earth's gravitational field in a non-linear way, perhaps creating a kind of gravitational inertia that could be harnessed. Others have drawn parallels to more modern, though still controversial, concepts like the M drive, wondering if the vibrations create a subtle interaction with quantum vacuum fluctuations. Of course, the simplest and most probable explanation remains that Norman Dean, whether intentionally or not, had created an exceptionally ingenious mechanical system that appeared to produce reactionless thrust by exploiting friction and surface interactions, but was in fact obeying Newton's laws perfectly. The real value of the Dean drive blueprint today lies not in its original claims, but in how modern technology allows us to finally put its principles to a definitive test. We now possess tools that Norman Dean could scarcely have imagined: High-speed cameras can track microscopic movements with incredible precision. Laser vibrometers can measure the exact frequency and amplitude of vibrations without ever touching the device. And most importantly, sophisticated force measurement systems like torsion pendulums operating in a vacuum can detect forces so minuscule they would have been invisible in the 1950s. Modern researchers can now build replicas based on the available blueprints and subject them to utterly rigorous testing, completely isolating the device from any external leverage. This would settle the debate once and for all. Furthermore, the core idea of using asymmetric vibrations for propulsion has found a new life in a different field: micro-robotics. Engineers are now developing tiny robots that use precisely controlled vibrations to walk across surfaces at a microscopic scale. While these devices are not reactionless, they push against the surface they are on. They demonstrate that the principle of directed motion from oscillation is a valid and powerful one when applied correctly. The Drive serves as a historical reminder of our fascination with breaking symmetry to achieve motion, a fascination that continues to drive innovation in both conventional and breakthrough propulsion research. This exploration of raw mechanical force provides a perfect contrast to our next concept, which harnesses a power source that is both ancient and utterly reliable: the light of the sun. After exploring the complex mechanical vibrations of the Drive, we now turn to a concept of beautiful simplicity, one that draws its power from the most reliable and abundant fusion reactor in our solar system, the sun. The blueprint for the solar thermal rocket is a masterpiece of elegant engineering. Imagine a spacecraft equipped not with a complex nuclear reactor or volatile chemical fuels, but with a gigantic, delicate mirror, unfurled in the silence of space like a technological flower. This mirror, perhaps hundreds of meters across, is precisely curved to focus the faint but constant light of the sun onto a single point, a heat exchanger containing a propellant, most likely liquid hydrogen. The principle is as straightforward as using a magnifying glass to start a fire, but on a cosmic scale. The concentrated sunlight heats the hydrogen to staggering temperatures, well over 2,500 degrees Celsius, turning it into a superheated plasma. This incredibly hot gas is then channeled through a traditional rocket nozzle, expanding rapidly to generate thrust. The beauty of this system lies in its efficiency. Because the energy comes from an external source, the sun, the spacecraft only needs to carry its propellant, not the fuel to heat it. This results in a specific impulse, a measure of rocket efficiency, that is roughly double that of the best chemical rockets, making it a highly effective engine for pushing large payloads across the inner solar system. This promising concept was born during the heady, optimistic dawn of the space age in the 1960s. As engineers dreamed of sustained operations between Earth, Mars, and the asteroid belt, the solar thermal rocket presented an irresistible vision: a spaceship that could refuel its propellant almost anywhere, powered by a source that would never run out. It was seen as the perfect workhorse engine for a true spacefaring civilization, enabling a constant, bustling traffic of cargo and crew. Designs proposed massive, rotating structures where the crew lived in a habitat module at one end of a long truss, with a giant mirror and engine assembly at the other, slowly spinning to create artificial gravity for the long voyage to Mars. It promised a future where space travel was not a series of explosive, all-or-nothing leaps, but a gradual, sustainable process of expansion, much like the age of sail gave way to steamships on the ocean. However, the immense engineering challenges of turning this elegant blueprint into a working reality quickly became apparent, causing it to be shelved in favor of more immediately attainable technologies. The first and most obvious hurdle was the mirror itself. Deploying a structure the size of several football fields in the zero-gravity and unforgiving vacuum of space is a monumental feat. The mirror would need to be incredibly lightweight to be launched from Earth, yet rigid enough to hold its precise parabolic shape without wobbling or distorting, as even a tiny imperfection would scatter the focused sunlight and drastically reduce efficiency. The materials available at the time, thin metallized polymers or fragile glass, were highly susceptible to damage from micrometeoroids and the intense temperature swings of space. A single puncture could render the entire system useless. Furthermore, managing the intense heat presented its own nightmare. The focal point of the mirror would be hotter than the surface of a blast furnace, requiring a heat exchanger made of materials that could withstand these temperatures for months on end without melting or degrading. While nuclear thermal rockets posed their own political and safety challenges, their reactors were compact and contained, making them seem like a more straightforward, if riskier, path compared to the daunting task of building and maintaining a fragile, city-sized mirror in orbit. For decades, the solar thermal rocket remained a promising idea on paper, overshadowed by the raw power of chemical rockets and the high-performance potential of nuclear systems. But today, this forgotten blueprint is experiencing a powerful revival, driven by a confluence of technological advances and a fundamental shift in our spaceflight goals. The modern push for in-situ resource utilization, the practice of living off the land in space, has made the sun's omnipresent energy more valuable than ever. For missions to Mars or asteroids where sunlight, while weaker than at Earth, is still a constant and free resource, the solar thermal rocket is an ideal candidate. The key enabler has been a revolution in materials science. We can now manufacture ultra-lightweight composite structures and membranes that are far more durable and resistant to the space environment. Imagine a mirror made from a thin, flexible polymer coated with a vapor-deposited layer of aluminum, supported by an inflatable or telescoping boom that rigidizes once deployed. These materials did not exist 50 years ago. Similarly, advanced ceramics and carbon-carbon composites developed for hypersonic aircraft and re-entry vehicles can now create heat exchangers that laugh at temperatures that would have vaporized earlier designs. This modern reassessment positions the solar thermal rocket not as a competitor to monstrous chemical boosters for launch, but as the perfect engine for the space-based leg of the journey. A spacecraft could be assembled in Earth orbit, its massive mirror deployed safely away from the stresses of launch, and then set sail for Mars. Once there, it could use the local sunlight to power its return trip, potentially even manufacturing its own hydrogen propellant from water ice found on the Martian surface or on a nearby asteroid. This changes the entire economics of exploration, reducing the need to launch every ounce of return fuel from the deep gravity well of Earth. The solar thermal rocket embodies a new philosophy of spaceflight, sustainable, efficient, and integrated with the environment of space itself. It is a testament to the idea that sometimes the most powerful solution is not the most complex one, but the one that harnesses a fundamental force of nature with grace and intelligence. This elegant reliance on an external power source stands in stark contrast to the philosophy of our next blueprint, which seeks to solve the propulsion problem by bringing the power of a star directly onboard the spacecraft. If the solar thermal rocket represents a graceful dance with an external power source, then our next forgotten blueprint is a declaration of war on the very limits of containment. We are about to cross a threshold into the realm of the extreme, to a propulsion concept so audacious it seeks to bottle a star and ride its fire. This is the gas-core nuclear thermal rocket, and it begins with a simple, terrifying question. What if we didn't just use nuclear fission to heat a propellant, but instead turn the propellant itself into the reactor core? The solid-core nuclear thermal rockets tested in the 1960s, like the American Nerva program, were already impressive. They worked by pumping a liquid propellant, like hydrogen, through a solid reactor core packed with uranium fuel elements. The hydrogen would be heated by the fission reaction and then blasted out the nozzle. But these systems had a fundamental limit: the melting point of the solid core itself. The fuel elements couldn't be heated beyond about 2,700 degrees Celsius without turning into a puddle of molten metal, which would destroy the engine and end the mission. This cap placed a firm ceiling on the rocket's efficiency. The gas core concept shatters that ceiling entirely. Its blueprint is a radical departure. Instead of solid fuel rods, the reactor contains its nuclear fuel-enriched uranium hexafluoride gas in a gaseous plasma state. The liquid hydrogen propellant is injected directly into this seething, fissioning cloud. Imagine a celestial forge, a volume of space where atoms are splitting apart with unimaginable fury, and right in the middle of this inferno, you spray a stream of hydrogen. The hydrogen is instantaneously heated not by conduction from a hot surface, but by direct contact with the nuclear fire itself. This allows the propellant to reach temperatures that are almost incomprehensible, up to 10,000, 20,000, or even 50,000 degrees Celsius. At these extremes, the specific impulse, the measure of a rocket's efficiency, skyrockets. Where a chemical rocket might manage 450 seconds and a solid-core nuclear rocket around 900, a gas-core system could achieve specific impulses of 3,000 to 5,000 seconds. This isn't a mere improvement, it's a transformation. A spacecraft powered by such an engine could reach Mars in a month, Jupiter in a few, and could make the outer solar system a regular destination for human exploration. The most visionary and poetic of these designs was the nuclear light bulb concept. This wasn't just an engine, it was a piece of scientific art. The blueprint called for containing the gaseous fission reaction, not with a physical wall, but with a wall of flowing propellant itself. The reactor would be a spherical or cylindrical chamber. The uranium plasma would be confined to the center, while liquid hydrogen was injected along the inner surface of the chamber's wall. This flowing hydrogen would form a cool, protective curtain between the hellish plasma and the physical wall of the reactor. But the true genius was the proposed material for the wall itself. It would be made of a transparent, high-temperature ceramic like quartz or sapphire. The idea was that the thermal energy from the plasma would radiate through this transparent wall as intense, pure light, like the filament of a light bulb, and be absorbed by the hydrogen propellant flowing on the other side. This elegant separation meant the propellant was heated by radiation, not by direct contact, which would hopefully keep the incredibly corrosive fission products contained within the central plasma ball. It was a dream of a clean, contained star, its light harnessed for propulsion. The reason this breathtaking blueprint was shelved, however, lies in the monumental, perhaps insurmountable, technical barriers it presented. Primary challenge was and remains containment. How do you hold a cloud of plasma that is hotter than the surface of the sun? The flowing hydrogen curtain and transparent wall of the nuclear light bulb were elegant theories, but in practice, the stability of such a system is a nightmare. The plasma would be subject to every kind of hydrodynamic and magnetohydrodynamic instability imaginable. Turbulence at the boundary between the plasma and the hydrogen curtain would inevitably cause chunks of the radioactive plasma to mix with the propellant and be ejected, making the engine dangerously dirty and inefficient. The second problem was the wall material itself. No known substance, even the most advanced ceramics of the 1960s, could withstand the combined assault of extreme neutron flux, intense ultraviolet radiation, and the staggering thermal stress for more than a few seconds. The transparent wall would likely darken, crack, or simply vaporize under the onslaught. The engineering required to maintain a stable, contained gaseous fission reactor was, and still is, considered one of the most difficult challenges in all of aerospace engineering. For half a century, the gas core rocket remained the ultimate what if of propulsion, a symbol of a power we could imagine but not command. But today, the context is shifting in ways that are prompting a serious re-evaluation. The single biggest enabling advancement comes from an adjacent field, nuclear fusion research. For decades, scientists working on tokamaks and other magnetic confinement fusion devices have been solving the very problem of how to hold a superhot plasma stable without letting it touch the walls. They have developed incredibly sophisticated magnetic field configurations that can pinch, twist, and control plasma with remarkable precision. Modern researchers are now asking if these same magnetic confinement techniques could be applied to a gaseous fission plasma. Instead of relying solely on a fragile hydrogen curtain, a gas core rocket could use a carefully designed magnetic bottle to keep the radioactive fireballs centered and away from the reactor walls. This hybrid approach could potentially solve the stability and corrosion issues that doomed the original concept. Simultaneously, the field of materials science has delivered breakthroughs that bring the nuclear light bulb's transparent wall back into the realm of possibility. Researchers are now developing new classes of ultra-high-temperature ceramics, transparent ceramics, and composite materials that are orders of magnitude more resilient than anything available in the 1960s. Materials like hafnium diboride or yttrium aluminum garnet transparent ceramics can withstand temperatures and radiation levels that were once pure fantasy. While the challenge remains immense, it is no longer considered a fundamental law of physics that it cannot be done. The gas core nuclear thermal rocket represents the absolute pinnacle of what might be achievable with fission-based propulsion. It is a concept that pushes against the very edge of material science and plasma physics, a testament to our enduring desire to harness the most powerful forces in nature. And this relentless push against the limits of containment logically brings us to a concept that represents the ultimate simplification: a propulsion system that does away with the reactor, the magnets, and the delicate containment altogether, choosing instead to ride the shockwave of a star itself. While the gas core rocket pushes the limits of containing a star's fury, our next forgotten blueprint proposes a far more direct and audacious approach. If you cannot contain a star, then why not simply ride the shockwave of a miniature one over and over again? This is the radical premise of inertial confinement fusion propulsion, a concept that turns the spacecraft itself into a fortress designed to withstand a relentless, self-inflicted bombardment of nuclear fire. The vision is both terrifying and magnificent, a vessel that journeys through the cosmos by detonating a succession of tiny hydrogen bombs mere meters behind its stern, each micro-explosion a fleeting, artificial sun whose blast wave pushes the ship forward. It is a form of travel that swaps the steady burn of an engine for the rhythmic pulse of controlled detonations, a cosmic cannonball fired not from a gun, but by its own internal explosions. The most famous and thoroughly studied incarnation of this idea was Project Orion, a serious initiative conducted in the late 1950s and early 60s. The blueprint for Orion was staggering in its scale and simplicity. The spacecraft would be massive, resembling a broad, domed city in space, with its most critical component being a gigantic, armored pusher plate attached to the rear by immense shock absorbers. The propulsion system was deceptively straightforward. It would eject small fusion bombs, each about the size of a beach ball, out of the back at a regular interval. A fraction of a second after ejection, the bomb would detonate. The resulting plasma fireball, expanding at a significant fraction of the speed of light, would slam into the pusher plate. The plate, made of a hardened material like tungsten or aluminum, would absorb the immense force of the blast, transferring it through the shock absorbers to the main body of the ship, providing a powerful push. The shock absorbers were the true genius of the design, smoothing out the violent, jerky impulses into a steady, manageable acceleration. Imagine a car driving over a continuous series of speed bumps. Orion's suspension system was designed to turn that bone-jarring ride into a smooth, forward glide. The performance figures dreamed up by the Orion team were unlike anything conceivable with conventional technology. By varying the rate of bomb detonations from 1 per second for a gentle acceleration to several per second for a rapid boost, the spacecraft could achieve astonishing speeds. Theoretical calculations suggested that an Orion-style ship could reach up to 10% of the speed of light, making a journey to Alpha Centauri, our nearest star system, a mission of just 40 or 50 years. This was not merely interplanetary travel. This was the first credible blueprint for an interstellar arc. The ship could be a veritable worldlet, weighing thousands of tons, carrying a crew of hundreds with ample shielding, supplies, and even artificial ecosystems for a multi-generational voyage. It was a vision of humanity moving into the galaxy not as tiny, fragile probes, but as a robust, traveling civilization. Across the Atlantic, a parallel but distinct concept emerged with the British project Daedalus in the 1970s. Daedalus refined the Orion blueprint, aiming for a fully automated interstellar probe. Instead of bombs with chemical explosives to trigger fusion, Daedalus proposed a more elegant, though equally challenging, method: inertial confinement fusion using pellets. The design called for a two-stage engine. In the first stage, electron beams would be fired into tiny pellets of a deuterium and helium-3 fuel mixture, compressing and heating them to fusion conditions. The resulting explosions would propel the spacecraft for several years. Then, the first stage engine would be jettisoned, and a second, smaller stage would take over to complete the acceleration. Daedalus was designed to be lighter and faster than Orion, a sleek robotic scout capable of reaching 12% of the speed of light and flying past Barnard's star within a human lifetime. Yet, for all their visionary promise, both Orion and Daedalus were ultimately shelved, victims of a potent combination of political fear and daunting engineering reality. The most significant obstacle was the Partial Test Ban Treaty of 1963, which prohibited nuclear explosions in the atmosphere, underwater, and in outer space. The very foundation of Orion's propulsion was an act that the world's superpowers had just agreed was too dangerous and environmentally destructive to permit. The political will to develop a technology based on setting off hundreds of nuclear bombs in space evaporated overnight. Furthermore, the environmental concerns were legitimate. While in deep space the fallout would be negligible, launching an Orion ship from Earth's surface would have been catastrophic, irradiating the launch site and surrounding areas. The engineering challenges were equally formidable. Designing a pusher plate and shock absorption system that could survive thousands of nuclear blasts without cracking or vaporizing was a material science problem of the highest order. For Daedalus, the challenge lay in the engine itself. Creating a reliable system that could ignite fusion pellets dozens of times per second with perfect precision for years on end was far beyond the technology of the 1970s. For decades, these concepts remained the ultimate examples of ideas that were too big, too bold, and too dangerous for their time. But the 21st century has breathed new life into this explosive blueprint thanks to two key areas of progress. The first is the dramatic advancement in laser fusion, or inertial confinement fusion. In recent years, facilities like the National Ignition Facility in the United States have achieved a major milestone: scientific energy gain, meaning they produced more fusion energy than the laser energy used to initiate the reaction. While this is a laboratory experiment and not yet a power plant, it proves that the fundamental physics of pellet fusion is sound. This breakthrough provides a much more controlled and elegant pathway to the kind of micro-explosions envisioned by Daedalus, using lasers instead of electron beams. The second enabling technology is advanced magnetic shielding. Instead of a physical pusher plate that must endure the brute force of the blast, modern concepts propose using a powerful magnetic field to contain the plasma fireball. The magnetic field would act as a cushion, interacting with the charged particles of the plasma to transfer momentum to the spacecraft without any physical contact, eliminating the problem of material erosion entirely. This modern reinterpretation is inspiring a new generation of designs, with names like Project Icarus and other interstellar studies. The dream of reaching the stars within a lifetime is no longer confined to the pages of science fiction. It is a subject of serious, if long-term, scientific inquiry. The inertial confinement fusion rocket represents the absolute apex of high-energy propulsion, a system that embraces the raw power of the nucleus to achieve velocities that humble all other technologies. It is a testament to human audacity, a willingness to contemplate riding the fire of creation itself to journey to new worlds. And this vision of harnessing cosmic power finds a fascinating counterpoint in a concept that is its utter opposite: a propulsion system that requires no explosions, no fuel, and moves with the silent, graceful patience of a sailing ship on a cosmic sea. After riding the shockwaves of miniature stars, we now turn to a method of travel that is the very definition of grace and patience. Picture a vessel that moves through the cosmos not with a roar, but with a profound and elegant silence, catching the wind of the sun itself. This is the principle of the magnetic sail, or mag sail, a blueprint that replaces volatile fuels and complex engines with a simple, expansive loop of wire. The concept is as beautiful as it is ingenious. A spacecraft would deploy a massive loop, perhaps dozens of kilometers across, made from a superconducting material. Once an electrical current is started in this loop, it would flow indefinitely without resistance, generating a powerful magnetic field around the spacecraft, much like the field that surrounds our own Earth. This magnetic bubble then becomes the ship's engine and sail combined. It does not push against anything solid. Instead, it pushes against the invisible, yet very real, stream of charged particles constantly blowing away from the sun, the solar wind. The solar wind is not a gentle breeze but a supersonic plasma, a flow of protons and electrons traveling at speeds of over 1 million miles per hour. When these charged particles encounter the magnetic field of the magsail, they are deflected. Just as a physical sailboat uses the wind's momentum to push its sails forward, the magsail uses the momentum of these particles. Each deflection imparts a tiny, continuous push on the magnetic field, which is transferred to the spacecraft. The thrust generated is incredibly gentle, far too weak to lift a ship from a planet's surface, but in the frictionless environment of space, where there is no drag to overcome, even this faint pressure can accumulate over time. A magsail-powered probe could accelerate for years, gradually building up tremendous speed without ever consuming a drop of propellant. Even more cleverly, the magsail can work in reverse. Upon approaching a distant star which has its own solar wind, the spacecraft could reorient its sail to use the new stellar wind as a brake. By turning the sail to face the direction of travel, the incoming particles would push against it, slowing the craft down dramatically and allowing for orbital insertion without the need for heavy retro-rockets. This makes the magsail one of the very few proposed technologies that can provide both propulsion and braking for an interstellar journey. The theoretical foundations for the magsail were laid down in the 1980s and 90s by visionary physicists like Robert Zubrin and Dana Andrews. They worked out the complex mathematics of plasma physics and magnetic field interactions, demonstrating that the concept was sound in principle. Their blueprints described vast, delicate loops that needed to be kilometers in diameter to interact with the solar wind effectively. However, this early work was immediately met with a major practical objection: the wire. To be feasible, the magsail required a superconducting cable that was not only incredibly long but also extraordinarily lightweight and capable of operating in the harsh temperature extremes of space. The superconductors available at the time, primarily niobium-titanium alloys, required cooling to near absolute zero with bulky, heavy systems of liquid helium. The mass of the cooling apparatus would have been so immense that it would have completely negated the advantage of having a propellantless drive. The magsail was therefore considered a fascinating but purely speculative idea, a solution waiting for a problem that technology had not yet solved. What has pulled this elegant blueprint from the realm of speculation into the sphere of serious design studies is the same revolution that is revitalizing so many forgotten concepts: the dramatic progress in materials science. The discovery of high-temperature superconductors in the late 1980s was the first crucial breakthrough. While still requiring cooling, these new ceramic materials could operate at the temperature of readily available liquid nitrogen, which is far easier and lighter to manage than liquid helium. But the real game-changer has been the more recent development of second-generation high-temperature superconducting tapes. These are not brittle wires but flexible ribbons, often made from a compound called yttrium barium copper oxide deposited on a metal substrate. They can carry immense current densities and are being manufactured in kilometer-long lengths for use in next-generation power grids and maglev trains. For a magsail, this is transformative. A spacecraft could carry a spool of this thin, flexible tape, deploying it in space to form a large, lightweight loop. The cooling system, while still necessary, can now be designed to be compact and highly efficient, using passive radiators and miniature cryocoolers. This modern reassessment has positioned the magsail as a leading candidate for the first true interstellar probes. While it may not deliver the high speeds of a fusion rocket, its virtues are unmatched for certain missions. Its slow but steady acceleration is perfect for a concept known as a generational probe, an unmanned spacecraft sent on a voyage lasting centuries to reach the nearest stars. It requires no dangerous nuclear material, and its power source can be simple solar panels while within the solar system. Agencies like NASA and private initiatives like Breakthrough Starshot are now actively studying scaled-down versions of the magsail for braking maneuvers. A small, high-speed probe launched by a powerful laser sail could carry a tiny magsail to deploy upon arrival at Alpha Centauri, using the star's plasma wind to slow down enough to make scientific observations rather than just flashing past in a matter of hours. The magsail embodies a philosophy of harmony with the space environment, using the resources that are already there. It is a quiet, patient technology for a future that thinks in terms of millennia, not mission timelines. This concept of sailing on an invisible medium finds a perfect partner in the idea we explore next, which also uses an external power source but applies it in a far more dynamic and forceful way. The sheer elegance of the magnetic sail, harnessing the sun's wind for a patient journey, presents a philosophy of harmony with the cosmos. But what if you crave speed? What if you need to cross the solar system not in years, but in weeks? This demand for velocity brings us to a blueprint that revisits the raw power of nuclear pulse propulsion, but with a crucial twist that aims to make it cleaner, safer, and far more precise. Welcome to the concept of external pulsed plasma propulsion, or EPPP. Imagine taking the terrifying yet magnificent fire of Project Orion and refining it, replacing the onboard atomic bombs with a scalpel instead of a sledgehammer. This is the core idea of EPPP. Generate the propulsive pulses not from dangerous material carried on the spacecraft, but from a remote, stationary source, beaming the energy to the vehicle as it travels. The blueprint for EPPP emerged in the late 20th century as a direct response to the obvious drawbacks of Project Orion. While Orion's performance was unparalleled, its reliance on setting off hundreds of nuclear explosions in space was a political and environmental non-starter. EPPP offered a sophisticated alternative. The spacecraft itself would be much simpler and lighter. Instead of a massive, armored pusher plate, it would need only a large, durable sail or a much smaller and lighter pusher plate. The real magic would happen back at the power source. This could be a gigantic laser array situated on Earth, perhaps built into a mountainside, or a massive solar-powered facility in orbit around the planet or the Sun. This stationary power plant would focus an unimaginably powerful beam of energy, either laser light or a stream of charged particles toward the departing spacecraft. As the spacecraft travels, it would release a series of small, inert pellets ahead of its path, almost like scattering gravel in front of a car. These pellets, made of a simple material like plastic or metal, would have no explosive properties on their own. They are just targets. A fraction of a second after a pellet is ejected, the remote power facility would fire its beam, striking the pellet with pinpoint accuracy. The energy transfer would be so instantaneous and intense that the pellet would not merely melt. It would be vaporized and transformed into a miniature plasma explosion, a ball of incandescent gas hotter than the surface of the Sun. This plasma cloud would then expand rapidly, slamming into the spacecraft's sail or pusher plate, imparting a powerful impulse of thrust. The process would then repeat over and over, ejecting a pellet, waiting for the beam to hit it, and riding the resulting shockwave, creating a rhythmic pulse of acceleration. The advantages of this externalized approach are profound. First and foremost, it eliminates the need to carry nuclear material, sidestepping the safety and political nightmares of Orion. The spacecraft becomes a much cleaner, simpler vehicle. Secondly, because the power source is stationary and potentially enormous, it is not constrained by the weight and size limitations of a rocket. It could draw power from massive solar arrays or even a ground-based nuclear reactor, providing a virtually unlimited energy supply for acceleration. This means the spacecraft could be accelerated for a much longer period, reaching speeds that would make trips to Jupiter or Saturn a matter of months rather than years. It transforms the propulsion system from a disposable engine into a reusable piece of infrastructure, a cosmic catapult that could launch many missions over its lifetime. However, the immense challenges that caused this brilliant blueprint to be shelved are just as dramatic as the concept itself. The primary obstacle is one of almost impossible precision. Hitting a small, rapidly moving pellet with an energy beam from a distance of thousands or even millions of kilometers is an aiming problem of astronomical difficulty. It would require a tracking and targeting system with unparalleled accuracy, capable of accounting for the finite speed of light and the precise position of both the spacecraft and the pellet. Any tiny error in timing or aim would cause the beam to miss its target entirely, wasting a colossal amount of energy and providing no thrust. the second monumental challenge is energy transmission. Sending a powerful beam of energy over interplanetary distances without it dispersing or being absorbed by the interstellar medium is a formidable task. The beam would need to be incredibly coherent and focused, and the transmitting optics would have to be nearly perfect to avoid diffraction that would blur the beam into uselessness. For the technology of the 1980s and 90s, these were not just difficult problems, they were considered virtually insoluble. Yet, the story of EPPP's modern rediscovery is a testament to how progress in one field can unexpectedly breathe life into a forgotten idea from another. The key enabling technologies that are making researchers look again at this concept are high-power laser arrays and advanced beam control. The development of phased array lasers, where thousands of smaller lasers act in perfect unison to create a single, steerable beam of immense power, has provided a potential solution to the aiming problem. These systems can adjust the beam's direction almost instantaneously without moving any large parts, using only electronic controls. Simultaneously, revolutionary advances in adaptive optics, technology used by astronomers to correct the blurring of starlight by Earth's atmosphere, now offer the ability to preemptively distort a laser beam in such a way that it will become perfectly focused by the time it reaches its distant target. This could compensate for the dispersion that plagued earlier concepts. This convergence of technologies has sparked a new wave of theoretical designs. Instead of envisioning a full-scale interstellar mission, modern proponents are looking at EPPP for rapid transit within the inner solar system, a laser facility on the Moon with no atmosphere to distort its beam could propel robotic cargo ships between Earth and Mars in a fraction of the time it takes with conventional rockets. The spacecraft would be simple, reusable freighters, needing only a sturdy sail and a mechanism to eject the pellets. Each pulse from the lunar laser would give them a kick, building speed until they reached their destination, where a similar facility could beam energy to slow them down for arrival. This vision transforms EPPP from a far-future fantasy into a plausible, infrastructure-based model for solar system logistics. A system where the highways are made of light and the fuel is beamed from fixed stations. This idea of divorcing the power source from the vehicle, of creating a network of energy that spacecraft can tap into, pushes our imagination to its limits, perfectly setting the stage for a concept that goes even further, proposing to manipulate not just energy, but the very geometry of space and time. But if beaming energy across space represents a form of cosmic infrastructure, our next blueprint proposes a far more radical kind of engineering, not of lasers or power grids, but of the very fabric of spacetime itself. We now cross the final frontier of theoretical physics to examine the wormhole induction drive, a concept that sounds like it was lifted from the most ambitious science fiction, yet is grounded in the same mathematical equations that describe the gravity holding our feet to the ground. The journey to this idea begins not in an engineer's workshop, but in the abstract world of geometry with Albert Einstein's theory of general relativity. In 1915, Einstein revealed that gravity is not a force in the traditional sense, but a consequence of the curvature of spacetime caused by mass and energy. Think of spacetime as a taut, flexible rubber sheet. A massive object like the Sun creates a deep well in that sheet, and the planets orbit by following the curved geometry of that well, like marbles rolling around a funnel. Einstein's field equations, the complex mathematical heart of this theory, have solutions that describe far more bizarre phenomena than simple gravity wells. In 1935, physicists Albert Einstein and Nathan Rosen explored one such solution that described a bridge connecting two distant points in spacetime, a shortcut or a tunnel. This theoretical structure became known as an Einstein-Rosen bridge, but we know it by its more popular name, a wormhole. The standard analogy is to take our rubber sheet representing the universe and fold it so two distant points touch. A wormhole would be a tiny tunnel piercing through the fold, creating a passage that could, in theory, allow for instantaneous travel between points that would otherwise be light years apart. For a spacecraft, this wouldn't be propulsion in the sense of accelerating through space. It would be a method of literally bypassing space altogether, redefining the very meaning of distance. The blueprint for a wormhole induction drive takes this cosmic shortcut and attempts to turn it into a practical engine. The visionary idea is that a sufficiently advanced civilization could, instead of traveling through space, manipulate the geometry of space around the spacecraft. The drive would work by generating unimaginable concentrations of energy to create, or more likely, locate and stabilize a microscopic, naturally occurring wormhole. It would then somehow expand this wormhole to a usable size and anchor one end of it to the spacecraft. The other end would be projected forward, ahead of the ship's intended path. The concept of induction comes into play as the drive would then pull on the spacetime at the far end of the wormhole, effectively dragging the entire local region of space, including the spacecraft, towards that point. From the perspective of the crew, the ship wouldn't be moving. Instead, the destination would be rushing towards them as space itself is reconfigured. It's the ultimate form of field propulsion, where you don't move through the field, you move the field itself. For decades after its theoretical discovery, the wormhole was dismissed as a mathematical curiosity with no bearing on reality, and the idea of a wormhole drive was considered pure fantasy. The reasons were twofold, and both were showstoppers. The first and most famous problem is stability. The kind of wormhole predicted by Einstein's equations would be incredibly unstable. It would be what physicists call a Schwarzschild wormhole, and it would collapse into a singularity, a black hole, in an infinitesimally short amount of time, far faster than even a single photon could pass through. To keep it open, theory suggests you would need a form of matter with a very strange property, negative energy density, often referred to as exotic matter. This isn't antimatter, which has positive energy. Exotic matter would have a repulsive gravitational effect, propping the wormhole's throat open against the immense force of gravity trying to crush it shut. In the 20th century, such a substance was considered completely hypothetical, with no known way to create or contain it. The second insurmountable hurdle was energy. The sheer amount of energy required to manipulate spacetime on this scale is almost beyond human comprehension. Early calculations suggested that to stabilize a wormhole just 1 meter in diameter, you would need to concentrate a quantity of negative energy equivalent to the mass energy of Jupiter, converted through some unknown process into this exotic form. The idea of harnessing the equivalent of a planet's mass just to open a doorway was so far beyond any conceivable technology that it relegated the wormhole drive to the absolute fringes of scientific discussion, a dream for physicists to ponder but not a goal for engineers to pursue. The modern rediscovery of this blueprint, however, is being fueled by two revolutionary developments that are slowly chipping away at these monumental barriers. The first comes from the ongoing quest for a theory of quantum gravity, an attempt to unify general relativity with the quantum mechanics of the very small. Theories like string theory and loop quantum gravity have provided new mathematical frameworks that allow physicists to explore the properties of wormholes in much greater detail. Within these frameworks, some solutions suggest that exotic matter might not be as impossible as once thought. Certain quantum field effects, like the Casimir effect we discussed earlier, have been shown to produce regions of negative energy density, albeit on a sub-microscopic scale. While this is a far cry from the Jupiter mass quantities needed, it provides a crucial proof of principle. The laws of physics may not explicitly forbid the existence of the exotic matter required to stabilize a wormhole. It transforms the problem from a question of "is it possible" to a question of "how could we scale it up?" A subtle but profound shift. The second, and perhaps more surprising, avenue of exploration comes from the world of metamaterials. These are artificial materials engineered to have properties not found in nature, such as a negative index of refraction for light. Scientists have discovered that the equations governing the flow of light through these complex metamaterials can be mathematically analogous to the equations describing the curvature of spacetime in general relativity. This has given rise to a new field called analog gravity, where researchers can create tabletop experiments that simulate the behavior of black holes, cosmic strings, and yes, even wormholes. By carefully designing a metamaterial structure, they can, in a limited sense, create an electromagnetic analog of a wormhole, guiding light waves in a way that makes them disappear at one point and reappear at another as if they had traveled through an invisible tunnel. This doesn't create a real gravitational wormhole, but it provides an incredible testbed for the mathematical principles involved. It allows us to experiment with the concepts of spacetime engineering in a lab, offering insights that could one day inform the design of a true gravitational propulsion system. The wormhole induction drive remains the most speculative concept on our list, a technology that may lie centuries or even millennia in the future. But its modern re-examination symbolizes the ultimate ambition of propulsion science, not to build a better rocket, but to ultimately master the geometry of the universe itself. But if the wormhole drive represents the ultimate theoretical leap, our next blueprint brings us back to a more tangible, though no less staggering, frontier of physics, the realm where matter meets its ultimate opposite. We have explored engines that burn fuel, engines that ride explosions, and engines that sail on light and magnetic fields. Now we venture into the domain of the most energy-dense reaction known to science, the annihilation of matter and antimatter. A pure antimatter rocket, which would direct the fury of total conversion into an exhaust plume, remains the holy grail of propulsion, offering efficiencies that dwarf every other concept. But its requirements are as extreme as its promise. This brings us to a more nuanced and perhaps more achievable compromise, a brilliant hybrid that tempers that raw power with a measure of control, the antimatter-catalyzed nuclear pulse propulsion system. Imagine you want to build a campfire. You could try to light a massive, damp log with a single match, a difficult and unreliable task. Or you could use that same match to light a small pile of dry kindling, which in turn would create a fierce, concentrated flame capable of igniting the large log. The antimatter-catalyzed engine follows this second, more intelligent path. Its blueprint is one of elegant initiation. The spacecraft would carry a conventional propellant, such as liquid hydrogen, much like a traditional rocket. It would also carry a minuscule supply of antimatter, perhaps just milligrams or even micrograms, stored in an incredibly sophisticated magnetic trap. To generate thrust, the engine would inject a tiny quantity of this antimatter, just a few billion atoms, into a chamber containing the hydrogen propellant. When a normal matter particle, like a proton from the hydrogen, meets its antimatter counterpart, an antiproton, they annihilate each other in a flash of pure energy. This annihilation is millions of times more energetic than a nuclear fission reaction. This sudden, localized burst of energy is not used to directly heat the propellant. Instead, it acts as the ultimate spark plug. The energy released by the matter-antimatter annihilation is so intense that it creates a fireball of gamma rays and pions, subatomic particles moving at nearly the speed of light. This radiation blast is then used to trigger a secondary, much larger reaction within the propellant itself. In one design, the propellant could be a fissile material like uranium-235. The pions from the annihilation would slam into the uranium nuclei, causing them to split in a fission chain reaction, which then heats the surrounding hydrogen into a plasma for thrust. In a more advanced version, the annihilation spark could be used to compress and heat a pellet of deuterium and tritium isotopes of hydrogen to the point of initiating nuclear fusion. In both cases, the antimatter is not the primary fuel. It is the exquisitely precise catalyst that unlocks the vast energy stored within a much more manageable and abundant conventional fuel source. The origins of this hybrid approach lie in the late 20th century, when scientists involved in projects like the American Interstellar Probe Study and Project Daedalus were grappling with the immense challenge of interstellar travel. They realized that while pure fusion or fission pulse propulsion was powerful, it required enormous amounts of heavy fuel. A pure antimatter rocket would be far more efficient, but the fantastical difficulty of producing and storing antimatter made it a distant dream. The catalyzed concept emerged as a brilliant middle ground. Studies showed that by using antimatter merely as a trigger, the total amount required for an interstellar mission could be reduced from kilograms, a production goal that would require planetary-scale factories, to mere grams, a quantity that, while still immensely challenging, began to look marginally conceivable within the laws of physics. It was an engineering solution to a physics problem, a way to leverage the ultimate power of antimatter without needing to command its full, unbridled force. For decades, this blueprint remained firmly in the category of speculative fiction due to two colossal, intertwined challenges: production and containment. The first problem is creating the antimatter itself. In nature, antimatter is vanishingly rare. It's produced in tiny quantities by cosmic rays and in particle accelerators. Facilities like Searl can produce antiprotons, but the rate is agonizingly slow. At current production rates, it would take many thousands of years and consume the entire planet's energy output to accumulate just a single gram. The process is incredibly energy inefficient. It takes far more energy to create an antiproton than you would ever get back from its annihilation. The second, equally daunting problem is storage. Antimatter cannot be allowed to touch any normal matter, not even the air in a container. The only way to hold it is in a perfect vacuum, suspended by incredibly complex magnetic fields in a device known as a penning trap. Any failure, any minute fluctuation in the magnetic field, and the antimatter would contact the wall of the trap, resulting in a violent explosion that would destroy the storage device. For a spacecraft, this meant carrying what amounted to a continuously armed bomb of unparalleled sophistication, a risk that seemed insurmountable. What has pulled this concept from the pages of theoretical studies into the realm of serious, long-term research is the slow, steady, and utterly remarkable progress being made in laboratories like Searl. The modern rediscovery is not about a sudden breakthrough, but about a gradual accumulation of capabilities that are turning science fiction into science possibility. Researchers are no longer just producing antimatter, they are learning to manipulate it with breathtaking precision. Experiments like the antiproton decelerator at Searl are dedicated to slowing down antiprotons so they can be studied and stored for longer periods. Scientists have successfully trapped clouds of antiprotons and even atoms of antihydrogen, an antimatter atom with an antiproton nucleus and a positron orbiting it, for minutes and then hours at a time. While this is a far cry from the years-long storage needed for a space mission, it demonstrates a fundamental understanding of the containment challenge that was pure guesswork just a few decades ago. Furthermore, research into more efficient production methods is ongoing. Concepts involving particle accelerators that recapture some of the energy used in creation, or novel ideas about collecting naturally occurring antimatter from planetary magnetic fields are being explored. The focus has shifted from asking, "Can we ever do this?" to "How can we make the process more efficient?" This change in mindset is crucial. It means that the antimatter-catalyzed nuclear pulse engine is now viewed as a technology pathway, a goal that might be achieved through a century of incremental advancement in particle physics and magnetic confinement technology, rather than an outright impossibility. It represents the pinnacle of controlled energy release, a system where the tiniest of sparks unleashes a stellar fire, offering a pathway to the stars that is both terrifyingly powerful and ingeniously efficient. This relentless pursuit of the perfect combustion process leads us directly to a blueprint that seeks to revolutionize the very definition of a rocket engine, not with exotic fuels, but with a smarter way to burn the conventional ones. After exploring the staggering potential of matter-antimatter annihilation, we now turn to a propulsion concept that proves a revolution doesn't always require exotic fuels. Sometimes it demands a radical rethinking of a process we thought we had mastered, combustion itself. For over a century, the fundamental principle behind almost every engine, from the one in your car to the mighty rockets that launch astronauts into orbit, has been a process called deflagration. This is a rapid but still subsonic burn. Think of the flame from a match or a gas stove. It's a fire that spreads through the fuel by heat conduction and diffusion. In a rocket engine, fuel and oxidizer are mixed and ignited, creating a hot, expanding gas that is funneled through a nozzle to generate thrust. It's a powerful and well-understood system, but it has inherent limitations. The combustion is often incomplete, leaving unburned fuel wasted, and the pressures achieved are ultimately constrained by the mechanics of a subsonic burn. Now, imagine replacing that familiar, spreading flame with something far more violent and efficient, a controlled explosion. Not a single, catastrophic blast, but a continuous, contained detonation wave traveling at hypersonic speeds, many times the speed of sound. This is the audacious goal of the Rotating Detonation Engine, or RDE. The fundamental blueprint for this revolutionary engine is surprisingly elegant in its geometry. Picture a ring-shaped channel like a hollow donut with one end open to a nozzle. Fuel and oxidizer are injected into this annular chamber along its inner wall. At a single point, the mixture is ignited, but instead of a flame that spreads out in all directions, the ignition is so powerful and precise that it creates a detonation wave, a self-sustaining shockwave front followed by a zone of incredibly rapid chemical reaction. This wave, a wall of supersonic fire and immense pressure, instantly consumes the fuel mixture in its path. Here's where the magic happens. This detonation wave doesn't just fade away. The geometry of the annular channel and the continuous injection of fresh propellant right behind the wave allow it to continue propagating, racing around the circumference of the chamber at speeds of up to 2,500 meters per second. As it travels, it compresses and ignites the new fuel mixture ahead of it, creating a sustained, spinning ring of detonation. The high-pressure exhaust gases from this continuous explosion are then funneled out of the open end of the channel through a nozzle, producing a tremendously powerful and, importantly, incredibly efficient thrust. The key advantage lies in the detonation process itself. Because the wave compresses the fuel mixture before burning it, the combustion is far more complete and happens at a much higher pressure than in a deflagration-based engine. This leads to a dramatic improvement in thermal efficiency, meaning you get significantly more push from the same amount of fuel. The fascinating aspect of this blueprint is that it is not a new idea. The fundamental principles were first proposed and investigated in the 1950s by pioneering engineers who saw the potential for a leap in performance. They recognized that containing a continuous explosion could be the key to unlocking a new regime of propulsion. However, the practical challenges of bringing this concept to life were so immense that it was quickly shelved. The primary obstacle was control. How do you initiate a detonation wave and then keep it stable, ensuring it travels smoothly around the channel without stalling, spinning out of control, or causing a catastrophic backfire into the fuel injection system? The physics of a sustained detonation are incredibly complex, involving a delicate balance between injection pressure, wave velocity, and combustion kinetics. The materials challenge was equally daunting. The engine chamber must withstand not just extreme heat, but also the relentless, repeated hammer blows of the detonation wave itself, a form of stress that would quickly fatigue and shatter the metals used in conventional rocket engines. With the technology of the mid-20th century, these problems appeared insurmountable, and the RDE was relegated to academic papers while the world moved forward with the more predictable, though less efficient, technology of deflagration. For decades, the rotating detonation engine remained a tantalizing theoretical concept, a solution in search of a problem that our tools couldn't yet solve. But the turn of the 21st century brought with it a convergence of technologies that has sparked a dramatic rediscovery. The single most important enabler has been the advent of supercomputers and advanced computational fluid dynamics software. Engineers can now create incredibly detailed simulations of the detonation process, modeling the behavior of the shockwave and the fuel mixture with a precision that was unimaginable 50 years ago. This virtual testing ground allows researchers to experiment with different chamber geometries, injection patterns, and ignition sequences without the cost and danger of building a physical prototype that might fail catastrophically. Armed with these digital insights, agencies like NASA, the U.S. Air Force Research Laboratory, and a host of private aerospace companies have begun building and testing successful RDE prototypes. In recent years, we have seen videos of experimental engines firing with a distinctive, sharp roar, a sound that is audibly different from the steady rumble of a conventional rocket. These tests have demonstrated stable detonation waves running for several seconds, a monumental achievement that proves the fundamental principle is sound. The material science challenges are also being met head-on. New manufacturing techniques, such as three-dimensional printing with advanced high-temperature superalloys and ceramic composites, allow for the creation of complex cooling channels within the engine walls that can withstand the brutal thermal and acoustic environment. The progress has been so rapid that some experts believe rotating detonation engines could be powering the upper stages of rockets within the next 10 to 20 years. The implications of this successful revival are profound. An RDE could be up to 25% more efficient than a traditional rocket engine of the same size. For a launch vehicle, this efficiency translates directly into increased payload capacity or extended range. A satellite launched by an RDE-powered rocket could carry more scientific instruments or station-keeping fuel, or it could reach a higher orbit without needing a larger, more expensive rocket. For deep space missions, the higher efficiency means faster transit times to other planets. The rotating detonation engine represents a paradigm shift, a move from burning fuel to harnessing controlled explosions. It demonstrates that sometimes the path to the future isn't found in a completely new discovery, but in revisiting an old idea with new eyes and superior technology, finally unlocking a potential that has been waiting patiently for its moment. This sophisticated mastery over combustion provides a fascinating contrast to our next concept, which achieves a different kind of optimization not through a new type of burn, but through a revolutionary redesign of the rocket nozzle itself. After mastering the violent efficiency of a continuous detonation wave, we arrive at a blueprint that approaches the problem of rocket performance from an entirely different angle. Instead of reinventing combustion, it reimagines the component that turns that fire into thrust, the nozzle. For over half a century, the bell-shaped nozzle has been the iconic silhouette of rocketry, from the V2 to the Saturn V to the Falcon 9. Its curved, widening form is designed to perfectly expand hot exhaust gases, accelerating them to supersonic speeds and pushing the rocket forward. But this classic design has a fundamental, built-in flaw. It's a one-trick pony optimized for a single, specific air pressure. A rocket launching from Earth's surface faces a dramatic journey. At sea level, the air is thick, pushing back against the exhaust plume with a pressure of 14.7 pounds per square inch. But as the rocket climbs, the atmosphere thins rapidly. By the time it reaches the vacuum of space, there is virtually no external pressure at all. A bell nozzle designed to work perfectly at sea level will be severely underexpanded in a vacuum. Its exhaust plume will balloon outwards uncontrollably, wasting energy and losing efficiency. Conversely, a nozzle optimized for the vacuum of space would be overexpanded at launch, causing the plume to separate unpredictably from the nozzle walls, creating dangerous vibrations and potentially ripping the engine apart. This is the rocketry equivalent of trying to design a single car engine that performs perfectly both at the bottom of the ocean and on the top of Mount Everest. The Aerospike engine, a blueprint that emerged as a brilliant contender in the 1960s and 70s, offers an elegant and radical solution to this altitude adaptation problem. Its design is a dramatic departure from the familiar bell. Instead of containing the exhaust gases within a curved wall, the Aerospike turns the entire concept inside out. Imagine a bell nozzle but sliced in half from top to bottom and then laid flat with its curved interior surface facing outward. This creates a wedge-shaped or conical central body, the spike around which the combustion occurs. The rocket's fiery exhaust is directed along the surface of this spike. Here's the genius: the outer boundary of the exhaust plume is not defined by a solid wall, but by the ambient air pressure itself. At sea level, the thick atmosphere presses against the plume, neatly contouring it to the spike's surface, acting as a virtual nozzle wall. As the rocket ascends and the external pressure drops, the exhaust plume naturally expands outward, continuously adjusting its shape to maintain optimal expansion against the thinning air. This automatic, self-adjusting property gives the Aerospike its key advantage. It maintains near-peak efficiency from the launch pad all the way to orbit, a feature known as altitude compensation. This inherent efficiency made the Aerospike a prime candidate for one of the most ambitious goals in aerospace, the Single Stage-to-Orbit Vehicle, or SSTO. The dream of an SSTO is a spacecraft that can launch from Earth, reach orbit, and return to land like an airplane, all without jettisoning any fuel tanks or booster stages. For such a vehicle, every ounce of weight and every percentage point of engine efficiency is critical. The Aerospike's ability to perform optimally across the entire flight profile meant it could, in theory, deliver more payload to orbit for the same amount of fuel compared to a cluster of conventional bell nozzle engines. Its compact, flat base also integrated more easily into the rear of a winged vehicle, reducing aerodynamic drag. During the development of the space shuttle, the aerospike was seriously considered, and it was a central feature of later experimental programs like the NASA X-33 Venture Star, a prototype for a fully reusable SSTO spacecraft. The promise was a future where access to space was as routine and economical as air travel, and the aerospike engine was the technological key meant to unlock that door. So why did this brilliant blueprint, with its compelling advantages, end up on the shelf for decades? The answer lies in the immense engineering challenges that its novel geometry introduced. The most formidable problem was cooling. In a traditional bell nozzle, the hot gases are contained within a wall that can be lined with a network of tiny channels. Fuel is circulated through these channels before being injected into the combustion chamber, absorbing heat and keeping the nozzle from melting. This technique, called regenerative cooling, is well established, but in an aerospike engine, the central spike is exposed to the full fury of the combustion process on all sides. Designing a regenerative cooling system for a complex, inward-facing spike structure, particularly at the vulnerable tip where the heat is most intense, proved to be a nightmare of fluid dynamics and materials science. The spike had to withstand temperatures that would vaporize most metals, and any failure would be catastrophic. The second major hurdle was structural integrity. A traditional bell nozzle is in essence a pressure vessel that contains the high-pressure exhaust, and its curved shape is inherently strong. The aerospike's central spike, however, is a cantilevered structure, like a diving board sticking out into a torrent of fire. It had to be strong enough to resist the immense forces trying to bend or break it, yet lightweight enough not to negate the engine's performance gains. Fabricating such a precise and robust structure with the manufacturing techniques of the 1970s and 80s was prohibitively difficult and expensive. Faced with these daunting technical obstacles and pressing budgets, program managers consistently fell back on the devil they knew, the simpler, proven, and more predictable bell nozzle. The space shuttle ended up using conventional main engines, and the X-33 project was ultimately cancelled, taking the aerospike's best chance for a real-world test with it. For years, the aerospike remained a fascinating footnote, a great idea that was too difficult to build. But the recent renaissance in private spaceflight, driven by a new willingness to tackle tough engineering problems for long-term gain, has brought this forgotten blueprint roaring back to life. Companies like SpaceX and Blue Origin, with their focus on fully reusable launch systems, are actively re-evaluating the aerospike for their next-generation vehicles. The modern engineering toolkit has capabilities that the original designers could only dream of. Advanced additive manufacturing, or three-dimensional printing, now allows for the creation of the spike's complex internal cooling channels in a single piece, using high-temperature superalloys that are far more resilient than those available decades ago. Sophisticated computational modeling can simulate the fluid structure interactions and heating profiles with incredible accuracy, allowing engineers to optimize the design on a computer long before metal is ever cut. The potential payoff for these new space pioneers is immense. A reusable rocket equipped with an aerospike engine would be significantly more efficient across its entire flight, meaning it could carry heavier payloads or reserve more fuel for precise landings and reuse. While the initial development cost is high, the long-term operational savings could be transformative, finally making the dream of single-stage to orbit a practical reality. The aerospike's revival is a perfect example of an old idea patiently waiting for the right technology and the right commercial ambition to converge. It demonstrates that a blueprint isn't forgotten forever. It's just waiting for its moment, for a new generation of engineers to arrive with fresh tools and the courage to solve the problems that stymied their predecessors. This pursuit of the perfectly adaptable engine naturally leads us to consider a propulsion concept that takes the idea of efficiency to its logical extreme, a vehicle that carries no engine at all, drawing its power from a remote source like a ship tapping into a distant lighthouse. The elegant adaptability of the Gyroscopic engine shows how refining a mature technology can yield incredible gains. But what if we could go a step further? What if we could remove the power source from the spacecraft entirely, making the vehicle itself dramatically lighter and simpler? This is the visionary promise of the beam-powered thermal rocket, a blueprint that turns the entire concept of a launch vehicle on its head. Imagine a spacecraft that sheds its most massive components, no complex turbopumps, no volatile fuel mixtures, and no heavy nuclear reactor. Instead, this vehicle is little more than a propellant tank, a heat exchanger, and a nozzle. Its power source remains firmly on the ground, or perhaps in orbit, a gigantic facility that projects a concentrated beam of energy, either microwaves or laser light, upward to meet the ascending craft. The principle is a masterpiece of simplicity. The spacecraft, often called a beamed thermal thruster, carries a supply of a simple, inert propellant, most likely liquid hydrogen. As it climbs, a ground-based transmitter of colossal scale tracks its trajectory with unerring precision. This transmitter fires a continuous, focused beam of energy that is captured by a collector on the spacecraft's underside. This collector is essentially a sophisticated mirror or antenna designed to absorb the beamed energy and transfer it, as intense heat, directly into the hydrogen propellant. The hydrogen is flash-heated into a super-hot plasma, which then expands violently through a traditional rocket nozzle to generate thrust. The vehicle is, in effect, a flying tea kettle, heated by a remote, wireless flame. The immense advantage of this system is captured in a fundamental rule of rocketry known as the mass ratio. By leaving the massive power plant on the ground, the spacecraft can be almost entirely dedicated to payload. This could slash the cost of launching material into orbit by a factor of 10 or even 100, transforming access to space from a monumental, expensive effort into a routine, affordable operation. During the 1970s and 80s, this concept was studied extensively by NASA and other research bodies, inspired by the vision of futurists like Gerard K. O'Neill. The potential for enabling large-scale space colonization, where materials for space habitats could be launched cheaply and frequently, was a powerful motivator. Designs envisioned massive, square-kilometer-sized antenna arrays in desert locations, beaming gigawatts of power to fleets of reusable launch vehicles. The appeal was undeniable. A single, permanent, and upgradable power infrastructure could serve an entire spacefaring economy, much like a single power plant can electrify an entire city. The spacecraft themselves would become relatively disposable, like commercial airliners but with far simpler mechanics, needing only to be refueled with hydrogen before their next flight. However, the technical showstoppers that consigned this brilliant blueprint to the archives were as formidable as the concept was elegant. The first and most critical challenge was the problem of aiming. Beaming energy over distances of tens or hundreds of kilometers through Earth's turbulent atmosphere is an optical nightmare. A laser or microwave beam, no matter how well collimated at the source, will spread out due to diffraction. Even more problematic, the atmosphere itself distorts the beam, causing it to shimmer and wander off target, an effect you can see when stars appear to twinkle in the night sky. For a beamed thermal system, missing the spacecraft's collector by even a small percentage would mean most of the colossal energy invested in the beam would be wasted, heating the empty air or, worse, posing a safety hazard to areas outside the launch corridor. The second monumental hurdle was thermal management on the vehicle. Concentrating gigawatts of power onto a collector the size of a swimming pool creates temperatures that rival the surface of the sun. Designing a heat exchanger that could absorb that energy and transfer it to the hydrogen without melting, vaporizing, or simply exploding was a material science challenge that seemed insurmountable with 1980s technology. The receiver would have to endure a thermal hell that made the inside of a conventional rocket engine seem temperate by comparison. For decades, these twin barriers of beam control and thermal survival kept the beamed thermal rocket firmly in the category of far future speculation. But today, a convergence of technologies from seemingly unrelated fields is solving these very problems, pulling this blueprint back into the realm of serious engineering. The revolution in aiming comes from two key areas: phased array lasers and adaptive optics. A phased array laser isn't a single giant laser, but a grid of thousands of smaller, individually controllable laser emitters. By minutely adjusting the phase of the light from each emitter, the entire array can electronically steer the combined beam almost instantly without moving any physical parts. This allows for incredibly precise, rapid corrections to compensate for atmospheric distortion. This is paired with adaptive optics, a technology perfected by astronomers for ground-based telescopes. A guide star or a laser beacon reflected from the spacecraft itself is used to measure the atmospheric distortion in real time. A computer then calculates the correction needed and deforms a special mirror in the beam path to preemptively cancel out the distortion, resulting in a stable, tightly focused beam that can lock onto a moving spacecraft with astonishing accuracy. Simultaneously, advances in high-temperature materials are tackling the thermal problem. Research on hypersonic vehicles and reusable rocket engines has produced new classes of ultra-high-temperature ceramics and carbon-carbon composites that can withstand thermal shocks and sustained heat that would have vaporized earlier materials. Engineers are also designing ingenious, open-cycle receivers where the propellant itself flows through porous walls, providing transpiration cooling, a self-healing, regenerative cooling system that uses the cold hydrogen to protect the very structure that is heating it. With these tools in hand, companies like Escape Dynamics and research groups at institutions like McGill University have built small-scale laboratory prototypes that successfully demonstrate the core principles. The focus has shifted from a giant system for launching humans to smaller, more immediate applications, such as beaming power to drones to keep them aloft indefinitely or launching small satellites with a ground-based laser. This incremental approach is building the necessary confidence and technology base, proving that beaming power for propulsion is no longer a fantasy but a credible pathway to a new era of spaceflight. This vision of a vehicle divorced from its power source, connected by an invisible thread of energy, represents a profound shift in our relationship with technology, a theme that finds its ultimate expression in our final and most speculative blueprint, a concept that seeks to manipulate not energy, but the very dimensions of spacetime. And so we arrive at the final, and perhaps most breathtaking, blueprint in our collection, a concept so deeply embedded in science fiction that its very mention evokes images of stars streaking past a cockpit window. Yet, the Alcubierre warp drive did not originate on a Hollywood storyboard. It was born from the rigorous mathematics of a theoretical physicist named Miguel Alcubierre in 1994. His goal was not to break the laws of physics, but to explore a clever loophole within them. Einstein's theory of general relativity famously states that nothing can travel through space faster than light. But Alcubierre asked a different question. What if, instead of moving through space, we could move space itself? His resulting blueprint describes a method where a spacecraft remains stationary inside a bubble, a region of flat space-time, while the fabric of the universe is manipulated around it. Specifically, space-time in front of the ship would be massively contracted, pulling the destination closer, while space-time behind the ship would be dramatically expanded, pushing the point of origin away. The ship itself would not be accelerating in the traditional sense. It would be surfing on a wave of distorted geometry, a wave that could, in theory, propagate faster than light without violating relativity. The vessel would simply ride this warp bubble like a surfer on a wave, arriving at its destination without ever having experienced the crushing forces of acceleration or the time dilation effects that plague near light-speed travel. For all its visionary brilliance, the Alcubierre drive was immediately recognized as a purely theoretical exercise, a fascinating but ultimately impractical solution. The reason lay in the astronomical energy requirements and a truly bizarre ingredient demanded by the equations: exotic matter. This isn't simply antimatter. Exotic matter would need to possess a property known as negative energy density or negative pressure. In essence, it would have a repulsive gravitational effect, something that has never been observed in a stable, large-scale form. The original calculations suggested that creating a warp bubble large enough for even a small ship would require an amount of negative energy equivalent to the mass energy of Jupiter, converted into this exotic form. Furthermore, the energy distribution needed to be perfect, forming a precise ring around the spacecraft. To the vast majority of the physics community, this was the ultimate deal breaker. Since exotic matter was considered a mathematical abstraction with no basis in reality, the Alcubierre drive was gently placed on the shelf of intriguing curiosities, a beautiful piece of mathematics that had no connection to the world of practical engineering. It was a blueprint for a castle in the sky, magnificent to behold but impossible to inhabit. The turning point, the moment this forgotten blueprint was pulled from the realm of pure theory and into the light of experimental science, began with a subtle but profound shift in perspective. Researchers started to ask if the requirements were quite as impossible as they first seemed. The first breakthrough was a recalculation of the energy needed. Later analyses, using more refined models, suggested that if the warp bubble could be made to oscillate or its shape optimized, the energy requirement could be lowered from a Jupiter mass equivalent to something more on the scale of the mass energy of a small spacecraft like the Voyager probe. While this is still an immense amount of energy equivalent to hundreds of kilograms of matter converted entirely to energy, it moved the goalposts from the physically impossible to the merely technologically monumental. The second and more crucial development came from quantum field theory. Physicists realized that while large, stable chunks of exotic matter don't exist, the laws of quantum mechanics do allow for negative energy densities on a microscopic scale. The Casimir effect, which we discussed earlier, is a prime example. The region between two closely spaced plates exhibits a negative energy density relative to the surrounding vacuum. This was a revelation. It meant that the exotic matter required by Alcubierre's equations might not be a mythical substance, but a real, albeit tiny and fleeting, quantum phenomenon. This theoretical crack in the door was enough to inspire a small group of courageous scientists to try and push it open. Most famously, a team at NASA Eagleworks Laboratory, led by Dr. Harold "Sonny" White, began a dedicated research program to explore the physics of warp fields. Their approach is not to build a prototype starship, but to conduct tabletop experiments designed to detect the telltale signs of a microscopic warp effect. Using a sophisticated instrument called a White-Jude warp field interferometer, they pass a laser beam through a region where they are attempting to create a minuscule distortion in spacetime, often by using the intense electric fields of a capacitor ring, a setup inspired by the work of Thomas Townsend Brown. The goal is to measure an infinitesimally small shift in the path of the laser light, a shift that would indicate a change in the local properties of space. These experiments are operating at the very edge of detectability, and the results are still debated within the scientific community. Yet, the mere fact that such experiments are being conducted at a premier aerospace institution represents a sea change. The Alcubierre warp drive is no longer just a mathematical toy. It is a hypothesis being tested, a forgotten blueprint that has become a catalyst for cutting-edge research into the fundamental nature of reality. It stands as the ultimate symbol of an idea that was too advanced for its time, now being re-evaluated with the bold curiosity that defines our era. What emerges from this grand tour of forgotten futures is not a story of random loss and lucky finds, but a distinct and powerful pattern. The journey of these 21 propulsion blueprints reveals that technological progress is far from a straight, predictable line. Instead, it moves in a great spiral where ideas are not discarded forever, but are revisited again and again, each time with a new set of eyes and a more advanced toolkit. The reasons these concepts were originally shelved are as consistent as the reasons for their modern revival, and understanding this rhythm is key to seeing the path ahead. The single most common thread tying these forgotten blueprints together is the simple, brutal reality of technological absence. An idea can be brilliant, its mathematics sound, and its vision breathtaking, but if the physical world lacks the means to build it, it remains a fantasy. For the gyroscopic inertial drive and the Biefeld-Brown effect, the necessary precision instruments to measure the infinitesimally small forces involved simply did not exist. Inventors like Keeley and Brown were trying to listen for a whisper in a hurricane with the tools of their day. For the Searl effect generator and the magnetic sail, the dream hinged on a material that could superconduct electricity at reasonable temperatures, a material that was nothing more than a theoretical wish for nearly a century. The nuclear saltwater rocket and the gas core systems were visions of power that demanded materials capable of containing a star's fury, materials that would not be invented for decades. These blueprints were not failures of imagination. They were prisoners of their time, waiting for the key of advanced materials science, nanotechnology, or supercomputing to unlock their potential. Alongside this waiting game for better tools, we see the immense influence of shifting scientific paradigms. The established consensus of any era acts as a gatekeeper, and ideas that challenge core principles are often met with deep skepticism, if not outright hostility. Proposals for reactionless drives like the Dean drive were dismissed as violations of Newton's laws, often without a thorough investigation. Concepts that hinted at a connection between electromagnetism and gravity, like the Biefeld-Brown effect, were marginalized because they did not fit neatly into the separate boxes physics had created for these forces. And theoretical leaps like the Heim theory were ignored because their complex, unique mathematical language was too difficult for the mainstream to translate and verify. A paradigm is a powerful lens for viewing the world, but it also creates blind spots. It takes a courageous scientist to look where the lens says there is nothing to see. Today, as we encounter persistent anomalies in cosmology and quantum mechanics, the scientific community is becoming more willing to re-examine those blind spots, to dust off old theories and see if they might contain pieces of a larger puzzle we are only now beginning to assemble. We cannot ignore the powerful, often decisive, role of economic and political priorities. The trajectory of innovation is rarely dictated by pure scientific curiosity alone. It is steered by the demands of the moment. The Cold War space race, for all its achievements, funneled immense resources into a very specific goal: achieving quick, dramatic victories in the contest for space. This favored proven, powerful chemical rockets over the long term, high-risk development of nuclear, thermal, or pulse propulsion. The Partial Test Ban Treaty of 1963, while a crucial step for global safety, effectively slammed the door on Project Orion by outlawing nuclear explosions in space. Economic pressures also played a part. During times of recession or when public interest waned, funding for speculative, long-term propulsion research was often the first to be cut. Why invest billions in an interstellar probe when there are pressing needs on Earth? This short-term thinking, while understandable, repeatedly stalled concepts that required decades of sustained investment. The modern era, with its surge in private spaceflight companies like SpaceX and Blue Origin, has introduced a new dynamic. These entities, driven by long-term commercial visions for space colonization and resource utilization, are often more willing to invest in foundational technologies that governments deem too risky or too far-term, creating a new engine for the rediscovery of these old ideas. This cyclical pattern of loss and rediscovery teaches us a humbling and exciting lesson about the nature of discovery itself. The path to the future is not about discarding the past, but about learning from it. Today's fringe science, today's crackpot idea, might simply be a concept waiting for its enabling technology to be invented or for a scientific paradigm to shift in its favor. The work of dismissed inventors like Thomas Townsend Brown or Norman Dean may not have been correct in its entirety, but they may have been observing real, subtle physical effects that they lacked the framework to explain properly. Their blueprints are not instructions to be followed blindly, but treasure maps pointing to areas of physics that we are now finally equipped to explore properly. This demands a more open-minded approach to speculative ideas, not an acceptance of them without evidence, but a willingness to investigate them with rigorous, modern tools before consigning them to the dustbin of history. The greatest breakthrough in propulsion might not be a brand new equation scribbled on a whiteboard tomorrow. It might be a faded diagram in a forgotten archive, waiting for us to finally understand its true language. We have traveled from gyroscopic curiosities to warp drives, witnessing how the scientific imagination of the past is being validated by the tools of the present. The key takeaway is that no idea is ever truly lost, it merely awaits its time. The rediscovery of these 21 propulsion blueprints reminds us that the path to the stars is paved with persistence, curiosity, and a willingness to learn from both the successes and dead ends of those who came before us. Let this be an inspiration to look at old problems with new eyes. What forgotten idea will you help bring back to life? Share your thoughts on which of these blueprints excites you the most in the comments below, and subscribe for more journeys to the edges of science and technology.